Hello and welcome. I'm glad you're here. Tonight we're going to explore one of the universe's most mysterious phenomena: black holes. These cosmic enigmas sit at the edge of what we can understand, where the rules of reality bend and break in the most extraordinary ways. They're objects so dense, so gravitationally intense, that not even light can escape their pull. And yet, for all their darkness, they illuminate some of the deepest questions we can ask about existence itself. Before we begin, I want to ask you something. How was your day? Whatever it held, whether it was filled with small victories or quiet struggles, moments of joy or stretches of weariness, I hope you'll take a moment to share it in the comments below. There's something comforting about knowing we're all here together, drifting towards sleep while contemplating the cosmos. And if you'd like more journeys like this one, please consider subscribing to the channel. It helps us create more of these gentle explorations for you. Now let's begin. The term black hole wasn't coined until 1967 by physicist John Wheeler, even though the concept existed for decades earlier. For years, decades really, scientists didn't know what to call these things. They had the mathematics, the predictions, the equations that suggested something impossibly strange could exist in the universe. But the name? That took time. Before 1967, physicists used terms like frozen stars, or dark stars, or gravitationally collapsed objects. These earlier names carry their own poetry, don't they? A frozen star sounds like something from a winter myth, something beautiful and terrible locked in eternal stillness. But then John Wheeler, a physicist with a gift for language as much as mathematics, offered a simpler phrase during a lecture: black hole. 2 words, direct, almost brutal in their clarity, and it stuck. The term captured something essential: the absolute darkness, the void-like nature of these objects. What's fascinating is that the name came so late in the discovery process. The concept had been lurking in the equations since Einstein's time, but it took half a century for someone to give it a name that felt right. Sometimes the hardest thing isn't solving the puzzle. It's finding the right words to describe what you found. Black holes aren't actually holes at all. They're extraordinarily dense objects with gravitational fields so strong that nothing can escape once it crosses a certain boundary. The name is misleading in a way. When you hear hole, you might imagine an opening, a tunnel, a passageway to somewhere else. And while some theories do play with the idea of black holes as gateways, the reality is both simpler and stranger. A black hole is an object. It's matter, an enormous amount of matter, compressed into an impossibly small space. Imagine taking something as massive as our sun and squeezing it down until it's just a few kilometers across. Or taking something even larger, millions or billions of times the sun's mass, and compressing it into a region smaller than our solar system. This compression creates gravity so intense that it warps the fabric of space-time itself. And there's a boundary around this compressed mass, an invisible sphere where the gravitational pull becomes so strong that not even light, traveling at 300,000 kilometers per second, can escape. That boundary is real, even though you couldn't touch it. It's not a surface made of matter, but a threshold carved into the geometry of space and time. Once you cross it, all paths lead inward. There's no turning back, no escape velocity that could save you. You're not falling through a hole. You're falling towards something so dense, so gravitationally dominant, that it's reshaped reality around it. The mathematical possibility of black holes was first predicted in 1916, just months after Einstein published his theory of general relativity. Picture this. It's 1916. The world is in the grip of World War I, and somewhere on the Russian front, a German physicist named Karl Schwarzschild is serving as a soldier. He's also doing something extraordinary. He's reading Einstein's newly published theory of general relativity, these revolutionary equations about how mass curves space-time, and he's working out the math. Not in a university office, not in a quiet library, but in the trenches, in the margins of wartime. Schwarzschild found an exact solution to Einstein's field equations. He calculated what space-time would look like around a perfectly spherical mass. And hidden in that solution was something unexpected. If you compressed enough mass into a small enough space, you'd create a region from which nothing could escape, a point of no return written into the mathematics of the universe. He sent his work to Einstein, who was astonished. Here was a solution Einstein himself hadn't found, delivered from a battlefield. Schwarzschild died less than a year later from an illness contracted during the war. He never knew that his solution would become the foundation for understanding black holes. He gave us the mathematics of the event horizon, the calculation of that boundary beyond which escape becomes impossible. All of this worked out in 1916, before anyone believed such things could actually exist in nature. For decades, many physicists, including Einstein himself, didn't believe black holes could actually exist in nature. The equations said it was possible. But possible and actual are different things, aren't they? For years after Schwarzschild's work, physicists looked at these solutions with skepticism. Einstein himself thought they were mathematical artifacts, interesting curiosities that wouldn't appear in the real universe. He published a paper in 1939 arguing that black holes couldn't form naturally. The idea seemed too extreme, too strange. Nature surely would find a way to avoid creating something so bizarre. This resistance is understandable, perhaps even endearing. These were brilliant minds confronting something that challenged their intuitions about reality. A region of space where time stops, where density becomes infinite, where the laws of physics as we know them break down. It's almost too much, too theatrical. And yet, the universe doesn't care about our intuitions. It doesn't design itself around what seems reasonable to us. It took observations, not just mathematics, to convince the scientific community. As telescopes improved and astronomers found objects behaving in ways that could only be explained by enormous, invisible masses, the evidence mounted. By the 1960s and 70s, the tide had turned. Black holes weren't just mathematical possibilities. They were real. They were out there, and we had found them. Sometimes reality is stranger than even our best minds can imagine it to be. The boundary around a black hole where escape becomes impossible is called the event horizon, a point of no return. The event horizon, even the name has a certain gravity to it, doesn't it? It's the boundary that separates the inside from the outside, the knowable from the unknowable. Cross it, and you're no longer part of our universe in any meaningful sense. You can still exist, still experience time passing from your own perspective, but you can no longer affect anything outside. No signal you send, no light you emit, no information you carry can cross back out. What's remarkable is that this boundary isn't a physical thing. There's no wall there, no membrane, no surface you could touch. If you were falling toward a supermassive black hole and crossed the event horizon, you might not even notice it happening. The space around you would look continuous, unbroken, but mathematically, geometrically, something profound has occurred. You've passed from a region where outward paths exist to a region where they don't. All roads now lead to the center, to the singularity. The event horizon is a point of no return written into the structure of space-time itself. The term event horizon is beautifully chosen. In navigation, the horizon is where you can see to, the edge of your visible world. An event horizon is similar. It's the boundary of events that can affect us. Anything happening beyond it is forever separated from our experience. It's a horizon not in space, but in causality itself. Black holes come in different sizes, from stellar mass black holes just a few times heavier than our sun to supermassive ones, billions of times the sun's mass. The universe has made black holes in a remarkable range of sizes. The smallest ones we know of, stellar mass black holes, are formed when massive stars die. They might be just 3 times the mass of our sun, maybe 5 times, perhaps 20 or 30. Still enormous by human standards, but relatively compact on cosmic scales. These are the black holes scattered throughout galaxies, the remnants of stars that burned brilliantly and then collapsed into darkness. Then there are the supermassive black holes. These are the monsters at the centers of galaxies, including our own. They're not 3 or 10 times the sun's mass. They're millions of times more massive. Billions in some cases. The black hole at the center of the Milky Way is about 4 million solar masses. The one in the galaxy M87, the first black hole ever photographed, is about 6.5 billion solar masses. These aren't just bigger stellar mass black holes. They're an entirely different category of object, so massive they've shaped the galaxies around them. And yet, despite this enormous range in mass, from a handful of suns to billions of suns, they all follow the same physics. They all have event horizons. They all warp space-time. They all obey Einstein's equations. There's something almost elegant about that. The universe has one set of rules for these objects, whether they're born from a single dying star or assembled over eons at a galaxy's heart. The first black hole candidate ever identified was Cygnus X1, discovered in 1964 through its X-ray emissions. In the constellation Cygnus, the Swan, there's a bright X-ray source. It was detected in 1964 by instruments carried on rockets. This was before we had X-ray telescopes in orbit. Astronomers noticed something peculiar about this source, which they named Cygnus X1. The X-rays were coming from a region of space where there was a visible star, a blue supergiant. But that star seemed to be orbiting something invisible, something massive. By tracking the star's motion, scientists could estimate the mass of its unseen companion, and the numbers kept pointing to something too heavy to be a neutron star, too dark to be anything ordinary. The conclusion was almost inescapable. It had to be a black hole, but saying it and believing it were different things. The evidence was compelling but indirect. You couldn't see the black hole itself, only its effects on nearby matter and light. Stephen Hawking, the legendary physicist, was skeptical enough that he made a famous bet with another scientist, Kip Thorne, in 1975. Hawking bet against Cygnus X1 being a black hole. He later conceded the bet in 1990 when the evidence had become overwhelming. There's something charming about that. A scientist willing to bet against his own field's discovery, and gracious enough to admit when the evidence changed his mind. Cygnus X1 is still there, still emitting X-rays as matter from the blue supergiant spirals into its dark companion. It was our first glimpse of these objects, and it opened the door to a new understanding of the cosmos. Nothing in the universe is darker than a black hole. It absorbs 100% of light that crosses its event horizon. Darkness, true darkness, is rarer than you might think. Most things that seem dark are actually reflecting at least a little light. A black piece of paper reflects a few percent. The darkest materials scientists have created in laboratories reflect fractions of a percent, but a black hole, it reflects nothing. Zero. Every photon that crosses the event horizon is absorbed, captured forever by the gravitational well. It's the only perfectly black object in existence. This perfect darkness is a consequence of the event horizon itself. Light that crosses that boundary can't turn around. It can't bounce back. It can only continue inward, toward the singularity. From outside, the black hole presents absolute blackness. Not the darkness of something that's poorly lit, but the darkness of something that allows no light to escape at all. There's something profound about this. In a universe filled with light, with stars and galaxies and cosmic radiation, black holes are the only places where light goes to die. They're voids in the most complete sense. And yet, paradoxically, they're often surrounded by some of the brightest phenomena in the universe. The brilliant accretion disks of matter spiraling inward, heating to millions of degrees, the brightest lights and the darkest darks existing side by side. It's a cosmic study in contrasts. The singularity at a black hole's center is a point where our current physics breaks down completely. At the very center of a black hole, according to general relativity, there's a singularity. This is where all the mass of the black hole is concentrated. Not in a small volume, but in a point of literally zero size. Infinite density, infinite curvature of space-time. It's where our equations stop making sense, where they produce infinities, where the math itself seems to scream that something is wrong. But here's the thing. Physicists don't really believe the singularity is physically real in that form. When your equations give you infinity as an answer, it usually means you're pushing the theory beyond its limits. General relativity is extraordinarily successful at describing gravity on large scales. But at the singularity, we're dealing with all the mass of a black hole compressed into a region smaller than an atom. That's where quantum mechanics should matter. And we don't yet have a complete theory that unifies quantum mechanics with general relativity. So the singularity is, in a sense, a placeholder. It's where we write, something happens here, without knowing exactly what. Maybe it's a region of quantum foam, where space-time itself fluctuates wildly. Maybe it's a strange form of matter we haven't conceived of yet. Maybe the question of what's at the center doesn't even make sense in the usual way. the singularity represents the edge of our knowledge, a place where our best theories politely step aside and admit they don't have all the answers. And there's something humbling about that. You can't see a black hole directly, but you can see its effects on nearby matter and light. Black holes are invisible. They emit no light, reflect no light. They're holes in the visible universe. But they're not undetectable. They're like a silent dancer moving through a crowded room. You might not see them directly, but you can watch how everyone else moves in response to their presence. When a black hole has a companion star, for instance, it can pull gas from that star. The gas doesn't fall straight in. It forms a swirling disk, an accretion disk, spiraling closer and closer to the event horizon. As the gas spirals inward, friction heats it to extraordinary temperatures, millions of degrees. At those temperatures, it glows brilliantly in X-rays. So we see this bright, hot disk surrounding nothing, a dark center. The black hole reveals itself through the light of the matter it's consuming. We can also detect black holes through their gravitational effects. Stars orbiting too fast around an invisible point. Light from distant galaxies bent and distorted as it passes near a massive dark object. Gravitational waves rippling through space-time when two black holes merge. These are the signatures of black holes, the ways they leave fingerprints on the universe around them. We've learned to read these signs, to infer the presence of something we can never see directly. It's detective work on a cosmic scale, piecing together the evidence to reveal something that hides in perfect darkness. The first actual image of a black hole wasn't captured until April 2019, showing the supermassive black hole in galaxy M87. For over a century, black holes existed primarily in mathematics and inference. We knew they were there, we could measure their effects, but we'd never seen one. Not really. And then, in April 2019, scientists revealed something extraordinary, an actual image of a black hole's shadow, backlit by the glowing material around it. The black hole they photographed sits at the center of a galaxy called M87, about 55 million light-years away. That's almost incomprehensibly distant. The light in that image had been traveling toward us since long before humans existed in our current form. To capture it, astronomers had to do something unprecedented. They linked radio telescopes from around the entire world, from Hawaii to Chile to Antarctica to Europe, and synchronized them to work as a single instrument. Effectively, they created a telescope as large as planet Earth itself. Even then, the image required years of data processing, algorithms sifting through petabytes of information to reconstruct what the black hole's shadow looked like. What they revealed was stunning in its simplicity, a bright orange ring of light surrounding a dark circle. That dark circle is the black hole's shadow, the region where light cannot escape. The ring is photons, particles of light, caught in orbit around the black hole, some escaping to reach us, creating that luminous halo. It's not a photograph in the traditional sense, but a composite image built from radio waves, and yet seeing it felt profound. After 100 years of theory and mathematics, we finally had a picture. We turned the invisible visible, if only at its edges. That famous 2019 black hole image shows a bright ring of light surrounding a dark shadow, the closest we can get to seeing a black hole. Look closely at that image from M87, and you'll notice something. The ring isn't uniform. One side is brighter than the other. This asymmetry tells a story. The black hole is spinning, and the brighter side is where material is rotating toward us. The Doppler effect, the same phenomenon that makes an ambulance siren sound different as it approaches and recedes, amplifies the light from that approaching side while dimming the receding side. The dark circle in the center is about 2.5 times wider than the actual event horizon. This is because light that passes too close to the black hole gets bent around and captured, even if it starts out slightly farther away than the horizon itself. So what we're seeing isn't the event horizon exactly, but the black hole's shadow, the region from which no light can reach us because it either fell in or was bent around and trapped. That bright ring is made of photons orbiting in the intensely curved space-time around the black hole. Some of these photons are in stable orbits, circling endlessly. Others are on trajectories that will eventually let them escape, carrying the image to our telescopes. The temperature in that region is staggering, billions of degrees. The material is moving at a significant fraction of the speed of light, and yet from 55 million light-years away, it appears as a serene orange glow, a ring of light around darkness. It's a portrait of gravity at its most extreme, rendered in radio waves and translated into colors our eyes can comprehend. Black holes have only 3 properties that can be measured from the outside: mass, spin, and electric charge. Here's something remarkable about black holes. They're simple, deceptively simple. Despite forming from complex objects, stars with intricate internal structure, with magnetic fields, with various chemical compositions, with turbulent atmospheres, black holes erase almost all of that information. From the outside, a black hole can be completely described by just 3 numbers: how massive it is, how fast it's spinning, and how much electric charge it carries. This simplicity is captured in a phrase that sounds almost whimsical: black holes have no hair. It's a technical term, but the metaphor works. Hair represents detail, texture, individual characteristics. Black holes have none of that. 2 black holes with the same mass, spin, and charge are identical, indistinguishable, regardless of what they formed from. You can't tell if a black hole was made from hydrogen or helium, from a massive star, or a merger of smaller black holes. All that complexity, all that history, gets smoothed away. This is both elegant and disturbing. Elegant because it means the mathematics of black holes is relatively clean. Disturbing because it suggests information gets destroyed, which bothers physicists deeply. In quantum mechanics, information is supposed to be conserved. The universe is supposed to keep a record of everything. But black holes seem to delete that record. They consume stars and gas and light, and all you're left with is mass, spin, and charge. Everything else vanishes behind the event horizon, seemingly lost forever. Most black holes probably have essentially 0 electric charge because they attract and neutralize opposite charges. In principle, a black hole could have an electric charge. The mathematics allows for it, but in practice it probably doesn't happen much. Here's why. If a black hole developed a significant positive charge, it would attract negative charges from the surrounding space: electrons, negatively charged ions, anything that could neutralize that charge. Similarly, a negative black hole would attract positive charges. The universe tends toward neutrality. This means that of the three properties that define a black hole, one of them is probably almost always zero. Electric charge doesn't seem to play a meaningful role in real astrophysical black holes, so we're really left with two numbers that matter: mass and spin. How heavy the black hole is and how fast it's rotating. These two properties shape everything about it: the size of the event horizon, the strength of frame dragging effects, the innermost stable orbit, the efficiency with which it can convert matter into energy. There's something elegant about this reduction. The entire personality of a black hole, if we can call it that, comes down to how much it weighs and how fast it spins. It's like describing a person by only their height and how quickly they walk. It seems impossibly reductive, and yet, for black holes, it's complete. Those two numbers tell you everything there is to know from the outside. The Schwarzschild radius is the distance from a black hole's center to its event horizon for a non-rotating black hole. Karl Schwarzschild's solution to Einstein's equations gave us a way to calculate the size of a black hole's event horizon. It's now called the Schwarzschild radius, and the formula is beautifully simple. For any given mass, there's a specific radius where, if you compress that mass inside it, it would become a black hole. The radius depends only on the mass. More massive objects have larger Schwarzschild radii. For an object with Earth's mass, the Schwarzschild radius is about 9 millimeters. Compress our entire planet, all its oceans and mountains and core and crust, into a sphere less than 2 centimeters across, and it becomes a black hole. Of course, this is wildly impractical. There's no force in nature that would compress Earth that way. But it illustrates the principle. It's not about mass alone, but about density, about concentrating mass into a small enough volume. The Schwarzschild radius scales linearly with mass. Double the mass, double the radius. This means supermassive black holes, despite being billions of times more massive than stellar ones, aren't billions of times denser. In fact, the average density inside a supermassive black hole's event horizon can be quite low, lower than water, even lower than air in some cases. The key is that all that mass is still contained within the Schwarzschild radius, creating an inescapable gravitational well. It's a reminder that black holes are defined not by crushing density everywhere, but by the relationship between mass and the size of the region it occupies. Our sun would need to be compressed to a sphere about 3 kilometers across to become a black hole. Imagine our sun, that massive ball of fusing hydrogen that lights our days and warms our world, somehow compressed down, not to planetary size, not to Earth size, but smaller still, down to about 3 kilometers in radius, 6 kilometers in diameter. That's roughly the distance you might walk in an hour. If all the sun's mass, 333,000 times Earth's mass, were squeezed into a sphere that small, it would become a black hole. This isn't going to happen, of course. Our sun doesn't have nearly enough mass to collapse into a black hole when it dies. It'll become a white dwarf instead, an Earth-sized ember, slowly cooling over trillions of years. But the thought experiment is instructive. It shows just how extreme the compression needs to be. We're talking about taking an object 1.4 million kilometers across and crushing it down to something you could fit inside a small city. The density required is almost beyond comprehension. And yet, this is what happens when the most massive stars die. Their cores, unable to resist their own gravity any longer, collapse in fractions of a second. The implosion is so catastrophic that nothing can stop it. Electron pressure fails. Neutron pressure fails. The core collapses past the Schwarzschild radius and becomes a black hole, while the outer layers explode outward in a supernova. In less time than it takes to blink, a stellar core transforms from matter we could theoretically understand to an object where our physics breaks down. The term spaghettification is the actual scientific term for what happens to objects falling into smaller black holes. Sometimes scientific terminology has a sense of humor. Spaghettification is a real term appearing in actual scientific papers, and it describes something both fascinating and horrifying. As you fall toward a black hole, the gravitational force on the parts of you closer to the black hole becomes significantly stronger than the force on the parts farther away. This difference in force, the tidal force, stretches you. For stellar mass black holes, which have relatively small event horizons, this tidal force becomes extreme well before you reach the horizon. If you fell in feet first, your feet would experience much stronger gravity than your head. You'd be stretched vertically and compressed. Horizontally, pulled into a long, thin strand like a piece of spaghetti. Hence the term. The stretching would continue, intensifying, until the molecular bonds holding you together simply couldn't withstand it anymore. You'd be torn apart at the atomic level, your constituent particles streaming toward the singularity in a thin thread. It's not a pleasant image, but it's honest physics. The same tidal forces that create ocean tides on Earth, the difference in the moon's gravitational pull on near and far sides of our planet, exist around black holes in vastly amplified form. The good news, if there is any, is that for supermassive black holes, this fate is delayed. We'll get to that in the next fact. But for stellar mass black holes, spaghettification is unavoidable and begins far outside the event horizon itself. For supermassive black holes, you could cross the event horizon without even feeling it at first. Here's where things get strange in a different way. The tidal forces that cause spaghettification depend not just on the black hole's mass, but on how close you are to it in absolute terms. For a supermassive black hole, millions or billions of solar masses, the event horizon is enormous. It might be millions of kilometers across, or even larger. And at that scale, the curvature of space-time at the horizon is relatively gentle. If you fell toward the supermassive black hole at the center of our galaxy, Sagittarius A, you would cross the event horizon without experiencing extreme tidal forces. From your perspective, space would seem mostly normal. You could look at your hands and see them intact. You could look around and see the universe outside, though it would appear increasingly strange due to the extreme curvature of light paths. You'd be falling, accelerating, but the immediate sensation wouldn't be one of being torn apart. Of course, this reprieve is temporary. As you continue falling inward, the tidal forces grow. Eventually, even with a supermassive black hole, you'd encounter regions where the tidal forces become extreme. But you'd have minutes, perhaps hours, between crossing the event horizon and reaching that point. Minutes or hours of falling through a region of space that's been cut off from the rest of the universe, unable to send signals out, condemned to continue inward. It's a gentler entry into oblivion, but the destination is the same. Black holes aren't cosmic vacuum cleaners. They don't suck things in any more than a star of the same mass would. This is a common misconception, fueled perhaps by the dramatic language we use around black holes. We talk about them consuming matter and light being trapped. But gravitationally speaking, a black hole is no different from any other mass. If you're orbiting a black hole at a safe distance, you're experiencing the same gravitational force you'd feel orbiting a star of the same mass at the same distance. Imagine if our sun magically, and we mean magically, since this can't actually happen, transformed into a black hole of equal mass. Earth wouldn't get sucked in. We'd continue orbiting exactly as we do now, at the same distance, at the same speed. The gravitational force depends on mass and distance, not on whether that mass is a glowing ball of plasma or a gravitational singularity. Of course, we'd all freeze in the darkness, since the sun would no longer be radiating heat and light. But gravitationally, nothing would change. Black holes only capture things that get too close, closer than they would need to be for a normal star. That boundary is the event horizon, which is much smaller than the surface of a star of the equivalent mass. So in a sense, black holes are more compact gravitational wells, but they're not more powerful at a distance. They don't reach out and grab things. They simply wait, exerting the same gravitational pull that any mass would, and consuming whatever happens to fall within their event horizons. The closest known black hole to Earth is about 1,600 light-years away, reassuringly distant on cosmic scales. Let's put this in perspective. 1,600 light-years means the light we'd see from that black hole, or rather, from material around it, left there 1,600 years ago. That's distant, very distant. On human scales, it's meaningless. On cosmic scales, it's actually relatively close, in our own galactic neighborhood, cosmically speaking. But it's far enough that we're in absolutely no danger. There might be closer black holes we haven't discovered yet, isolated ones without companion stars or accretion disks to make them visible. They could be wandering through the galaxy invisibly, dark and silent. But even if there were 100 light-years away, it would pose no threat. Remember, black holes don't reach out and grab things. They don't expand their influence over time. They're just massive objects sitting in space, affecting things nearby, but leaving distant objects alone. The universe is vast, and black holes, while numerous, are scattered widely. The nearest stellar mass black holes are far enough away that they're curiosities to study, not hazards to fear. We can contemplate them safely, explore their properties through telescopes and mathematics, ponder their mysteries without any existential threat. They're out there in the cosmic dark, doing their slow work of warping space-time, and we're here, comfortably far away, trying to understand them. Stellar mass black holes form when massive stars, at least 20-25 times the sun's mass, exhaust their nuclear fuel and collapse. Stars are engines of balance. For most of their lives, they maintain an elegant equilibrium between two opposing forces, gravity pulling inward, trying to collapse the star, and the outward pressure from nuclear fusion in the core, pushing back. As long as a star has fuel to burn, hydrogen fusing into helium, then helium into heavier elements, it can maintain this balance. It's a standoff that can last millions or billions of years, but eventually, even the most massive stars run out of fuel. When a star much larger than our Sun reaches this point, it has already fused elements up through iron in its core, and iron is where the process stops. Fusing iron doesn't release energy, it consumes energy. So when the core becomes iron, there's no more outward pressure to hold the star up. Gravity wins. Suddenly, catastrophically, the core collapses. The outer layers follow, falling inward at speeds approaching a quarter of the speed of light. In less than a second, perhaps just milliseconds, the core that was once hundreds of thousands of kilometers across compresses down past the Schwarzschild radius. What happens next depends on the star's mass. If the core is massive enough, nothing can stop the collapse. Not electron degeneracy pressure, which holds up white dwarfs. Not neutron degeneracy pressure, which holds up neutron stars. The collapse continues past all possible stopping points through the event horizon toward the singularity. A black hole is born, typically while the star's outer layers explode outward in a supernova. It's a violent creation, a cosmic death transformed into something even stranger than the star that preceded it. Not all dying stars become black holes, only the most massive ones do. The fate of a star is written in its mass from the very beginning. Smaller stars, like our Sun, will die gently. In about 5 billion years, the Sun will swell into a red giant, then shed its outer layers into space, leaving behind a white dwarf, a hot, dense core about the size of Earth, slowly cooling over trillions of years. No drama, no collapse, no black hole. Just a gradual fading. Stars several times more massive than the Sun can end as neutron stars. When their cores collapse, they compress matter to extraordinary densities. A teaspoon of neutron star material would weigh as much as a mountain. But they stop short of becoming black holes. The pressure from neutrons squeezed together, resisting being packed any tighter, is enough to halt the collapse. These neutron stars are exotic objects in their own right, sometimes becoming pulsars that sweep beams of radiation across space, like cosmic lighthouses. But the truly massive stars, those born with at least 20 or 25 solar masses, face a different destiny. Their cores are so heavy that when fusion stops, nothing in the known universe can prevent the collapse from continuing past the event horizon. They're doomed, in a sense, from birth. Their very massiveness guarantees they'll become black holes. It's worth sitting with that thought for a moment, that some stars are born already destined to end as regions of space-time from which nothing can escape. The universe creates these objects not by accident, but as a natural consequence of stellar evolution. The supernova explosion that creates a stellar black hole can briefly outshine an entire galaxy. Picture a galaxy containing 100 billion stars, each one a sun, many of them far more luminous than ours. Now imagine a single exploding star that, for a few weeks, shines as brightly as all of them combined. That's a supernova. The energy released is almost incomprehensible. In the span of a few seconds during the core collapse, more energy pours out than the star emitted during its entire previous lifetime. Most of this energy escapes as neutrinos, ghostly particles that barely interact with matter and stream away at the speed of light. But enough energy remains to blow the star's outer layers into space at thousands of kilometers per second. The explosion creates heavy elements: gold, platinum, uranium, all the elements heavier than iron, and scatters them into the cosmos. These enriched gases eventually become part of new clouds, new stars, new planets. The calcium in your bones, the iron in your blood, the oxygen you breathe, much of it was created in supernova explosions. And yet, for all this light and violence, the core that collapses to form a black hole does so in relative darkness. The implosion happens so fast that even light can't escape once the event horizon forms. So you have this paradox. The brightest explosion in the universe creates the darkest object. The star goes out in a blaze of glory, seeding the cosmos with the raw materials for future worlds, while at its heart, a black hole forms in silence, a permanent scar in space-time, marking where the star used to be. We still don't fully understand how supermassive black holes formed in the early universe. They appeared surprisingly quickly. Here's a puzzle that keeps astrophysicists awake at night. When we look at the very distant universe, looking back in time to when the universe was less than 1 billion years old, we find quasars. These are supermassive black holes, billions of times the sun's mass, actively feeding and shining brilliantly. But how did they get so massive so quickly? If you start with a stellar mass black hole from a dying star, it has to grow. It can consume nearby matter, sure, but there's a limit to how fast it can grow called the Eddington limit. Radiation pressure from the infalling matter pushes back against gravity, slowing the rate of accretion. Growing from a few dozen solar masses to 1 billion solar masses, even at the maximum rate, should take longer than the age of the universe at the time these quasars existed. So either these black holes were feeding faster than we think possible, violating or circumventing the Eddington limit somehow, or they started much larger. Maybe instead of forming from stars, some supermassive black holes formed directly from collapsing clouds of primordial gas in the early universe. Maybe they formed from clusters of stars collapsing together. Maybe there are mechanisms we haven't thought of yet. This is an active area of research, with new theories and observations constantly refining our understanding. But for now, the early appearance of supermassive black holes remains one of cosmology's beautiful mysteries. There's likely a supermassive black hole at the center of nearly every large galaxy, including our own Milky Way. This was a shocking discovery when astronomers first realized it. As observations improved through the late 20th century, it became clear that massive dark objects lurked at the centers of most galaxies. Not some galaxies, not most galaxies, but essentially all large galaxies. The correlation is so strong it suggests a deep connection between galaxies and their central black holes. Our own galaxy, the Milky Way, has one. We call it Sagittarius A, or SGR-AO for short, because it's located in the direction of the constellation Sagittarius. For years, astronomers tracked stars orbiting this invisible object at the galaxy's core. These stars move at incredible speeds, thousands of kilometers per second, in tight elliptical orbits. By measuring their motions with exquisite precision, scientists calculated the mass of the object they're orbiting, about 4 million times the Sun's mass, concentrated in a region smaller than our solar system. Nothing but a black hole could be that massive and that compact. The existence of these supermassive black holes at galactic centers raises profound questions. Did the black hole form first, then attract matter that became the galaxy? Or did the galaxy form first, and the black hole grew from material that collected at the center? Or did they grow together, each influencing the other's development? The answer seems to be the latter. They co-evolve. Galaxies and their central black holes are intimately linked, their fates intertwined in ways we're still working to understand. It's a cosmic partnership that's existed for billions of years. Our galaxy's central black hole, Sagittarius A, has a mass of about 4 million suns. 4 million solar masses sounds enormous, and it is. But here's something that puts it in perspective. Despite this tremendous mass, Sagittarius A is remarkably quiet. It's not actively consuming large amounts of material right now. It's not blazing as a quasar. It's relatively dormant, sipping rather than gulping from its surroundings. We know it's there because of the stars orbiting it, some of which have been tracked for decades. One star, called S2, has an orbital period of just 16 years. That means astronomers have watched it complete multiple full orbits around the black hole. At its closest approach, S2 comes within 17 light hours of the event horizon. That's closer than our outermost planets are to the Sun, and reaches speeds of about 3% the speed of light. These observations have allowed incredibly precise measurements of the black hole's mass and have even tested Einstein's general relativity in the strong field regime. Imagine being on a planet orbiting S2, if such a planet could exist. Every 16 years, you'd swing close to a supermassive black hole, close enough that time dilation effects would be measurable, close enough that you'd see the fabric of space-time visibly warped. Then you'd swing back out into the relative calm of the outer regions, only to return again in another orbit. It's a cosmic environment so extreme it challenges our ability to imagine it, and yet it's right there at the center of our home galaxy. Black holes can grow by consuming nearby matter or by merging with other black holes. Growth, for a black hole, is straightforward in principle. Anything that crosses the event horizon adds its mass to the black hole. A passing cloud of gas, a wandering star, another black hole, it all contributes. The black hole gets heavier, its event horizon expands slightly, and the process continues. Over millions or billions of years, a black hole can grow substantially just by being in the right location, at the center of a galaxy where matter is relatively abundant. But there's another growth mechanism that's more dramatic: merger. When two black holes spiral together and combine, you instantly create a larger black hole. This isn't a gentle process. As the black holes orbit each other, they emit gravitational waves, ripples in space-time itself, that carry away energy and angular momentum. This loss of energy causes the orbit to decay. The black holes spiral closer and closer, orbiting faster and faster, until finally they merge in a fraction of a second. What's remarkable is that we can now detect these mergers. The gravitational waves they produce travel across the universe at the speed of light, and when they reach Earth, they cause space itself to stretch and compress by tiny amounts. Detectors like LIGO can measure these changes and reconstruct what happened billions of light years away and millions or billions of years in the past. Each detection is a window into one of the universe's most violent events, and each one represents a black hole growing by swallowing another black hole whole. When two black holes spiral together and merge, they lose up to 5% of their combined mass purely as gravitational wave energy. Think about that for a moment. When two black holes merge, the final black hole has less mass than the sum of the two that combined. Where did that mass go? It was converted entirely into gravitational waves, ripples in the fabric of space-time that propagate outward at the speed of light. Einstein's famous equation E=mc2 applies here. Mass is converted to energy with perfect efficiency. 5% might not sound like much, but when you're talking about black holes with tens of solar masses, 5% is more than an entire sun's worth of mass converted to pure energy in a fraction of a second. The peak power output during the merger can exceed the combined light output of every star in the observable universe. Not the combined mass, the combined light output. For that brief instant, the merging black holes are the brightest gravitational event in the cosmos, though they produce no electromagnetic radiation at all. This energy radiates away as gravitational waves, stretching and squeezing space-time as they pass. By the time they reach Earth, they're incredibly weak. They change lengths by less than the width of a proton across distances of kilometers. But we can measure them. We can hear the chirp of the merger in the data, the increasing frequency as the black holes spiral faster, then the ring down as the merged black hole settles into its final state. It's one of the most extraordinary measurements in modern science, detecting ripples in space-time from cataclysms that happened when the universe was younger. Intermediate mass black holes, between stellar and supermassive sizes, are the hardest to find and confirm. We have good evidence for stellar mass black holes, from a few to 100 solar masses or so. We have excellent evidence for supermassive black holes, from millions to billions of solar masses. But in between, that's where things get murky. Intermediate mass black holes, those with hundreds to hundreds of thousands of solar masses, are elusive. This is partially an observational challenge. They're not massive enough to dominate the centers of large galaxies like supermassive black holes do, but they're too massive to form easily from a single stellar collapse. If they exist in significant numbers, they might be wandering through galaxies, invisible unless they happen to be feeding on matter. Or they might exist in smaller galaxies or dense star clusters. We have some candidates, some tantalizing hints from observations, but few confirmed examples. Theoretically, intermediate mass black holes are interesting because they might be the seeds that grew into supermassive black holes. Or they might form from the repeated mergers of stellar mass black holes in dense environments. The uncertainty around them represents a gap in our understanding of black hole populations. It's like knowing about mice and elephants, but not being sure whether any medium-sized mammals exist. We're fairly confident they're out there somewhere. We just haven't figured out how to reliably find them yet. Some theories suggest tiny primordial black holes might have formed in the first moments after the Big Bang. Most black holes form from the deaths of stars, billions of years after the Big Bang. But what if some black holes are as old as the universe itself? In the first fractions of a second after the Big Bang, the universe was incredibly dense and hot, with matter and energy distributed unevenly. In regions where density fluctuations were particularly extreme, gravity might have overcome other forces and created black holes directly. No stars required. These primordial black holes could have a huge range of masses, depending on the size of the density fluctuation that created them. Some might be tiny, with masses less than a planet. Others could be much larger. The interesting thing is that primordial black holes wouldn't need to form from collapsed stars, so they could exist at masses where stellar black holes can't, filling in the gaps in the mass spectrum. There's even speculation that primordial black holes could make up some or all of dark matter, the mysterious invisible mass that seems to comprise most of the matter in the universe. It's a compelling idea. Dark matter isn't an exotic particle, but rather a population of ancient, invisible black holes wandering through galaxies. We don't have definitive evidence for this yet, but it's an active area of research. It's possible that some of the universe's first structures weren't stars or galaxies, but black holes, born in the cosmic fireball of creation itself. Black holes don't live forever. They very slowly evaporate through a process called Hawking radiation. In 1974, Stephen Hawking made a discovery that shocked the physics community. He showed that black holes aren't entirely black after all. They emit radiation. Very faint, very cold radiation, and in doing so, they slowly lose mass. This was revolutionary because it connected quantum mechanics, which governs the behavior of particles, with general relativity, which governs gravity and space-time. Black holes, it turned out, sit at the intersection of these two great theories. The mechanism is subtle. In quantum mechanics, empty space isn't really empty. It's filled with virtual particle pairs that pop into existence and annihilate each other almost instantly. Near a black hole's event horizon, something strange can happen. One particle of a virtual pair can fall into the black hole, while the other escapes. To an outside observer, it appears as though the black hole has emitted a particle. This emission carries away energy, and since energy and mass are equivalent, the black hole loses mass in the process. Hawking radiation means black holes evaporate. Extremely slowly, to be sure. So slowly that for any black hole we can observe, the evaporation is utterly negligible. But in principle, given enough time, any black hole will eventually radiate away its entire mass and disappear. It's a poetic thought in a way. These objects that seem so permanent, so absolute in their darkness, are actually slowly returning their borrowed mass to the universe, particle by particle, over timescales that dwarf the age of the cosmos. A black hole with the mass of the sun would take about 1067 years to evaporate completely. Let's try to grasp this timescale. The universe is currently about 13.8 billion years old. That's 1.38 x 10 more 10 years. A solar mass black hole would take 10 to 67 years to evaporate. That's a 1 followed by 67 zeros. To put that in perspective, it's 1057 times longer than the current age of the universe. It's a number so large it loses meaning. Long before a stellar mass black hole could evaporate, the universe will have changed beyond recognition. All the stars will have burned out. Galaxies will have dispersed. The cosmic microwave background will have redshifted into invisibility. We'll be in what cosmologists call the black hole era of the universe, when black holes are among the last remaining structures. And even then, they'll persist for almost unimaginable durations. The rate of evaporation depends on the black hole's size. Smaller black holes evaporate faster because they have higher surface temperatures. But even a black hole with the mass of a mountain, far smaller than any we've observed, would take billions of years to evaporate. For the supermassive black holes at the centers of galaxies, the evaporation time stretches into 100 years or more. These are timescales so vast that the phrase essentially forever almost feels appropriate, even though technically, mathematically, forever is something else entirely. Smaller black holes evaporate faster than large ones. If tiny enough, they could theoretically explode. Here's where Hawking radiation gets interesting. The temperature of the radiation, and thus the rate of evaporation, is inversely proportional to the black hole's mass. Massive black holes are incredibly cold, with temperatures far below the cosmic microwave background. They actually absorb more radiation from space than they emit, so they grow slightly rather than shrink. But smaller black holes are hotter. As a black hole evaporates and loses mass, it gets hotter, which makes it evaporate faster, which makes it hotter still. It's a runaway process. In the final moments of a black hole's life, when it's down to a relatively small mass, it evaporates explosively. A black hole with the mass of a large mountain would have a temperature of billions of degrees and would evaporate completely in about a second, releasing as much energy as millions of nuclear bombs. We've never observed such an explosion, which makes sense. Primordial black holes with masses small enough to be evaporating now would have had to form in the early universe and would be incredibly rare. But theoretically, they could be out there. Occasionally, astronomers look for the telltale gamma-ray signature of an evaporating black hole. So far, none have been found. But the search continues, because detecting one would be an extraordinary confirmation of Hawking's prediction and would open a window into quantum gravity. As a black hole evaporates, it gets hotter and radiates faster in a runaway process. Imagine the final days of a black hole, if we can call them days. After trillions upon trillions of years of slow, gradual evaporation, the black hole has shrunk to a fraction of its original mass. It's still a black hole, still has an event horizon, but it's much smaller now, and it's radiating more intensely. As the mass continues to decrease, the temperature rises. The black hole begins to glow more brightly in gamma rays. The evaporation accelerates. What took eons at the beginning now happens in centuries, then years, then seconds. The final moments are a brilliant flash of energy as the last remnants of mass convert to radiation. In an instant, the black hole is gone, leaving behind only photons streaming away at the speed of light. What remains afterward is an open question. Some theories suggest there might be a stable remnant, a tiny object with a minimum mass that can't evaporate further. Others suggest the black hole disappears completely, leaving nothing behind but the radiation it emitted. The answer depends on physics we don't fully understand yet: quantum gravity, the behavior of space-time at the smallest scales. But one way or another, the black hole's long journey ends not with a whimper, but with a bang, a final act of defiance against the darkness. The energy for Hawking radiation comes from the black hole itself, slowly reducing its mass. This is what makes Hawking radiation so remarkable from a conservation standpoint. The energy doesn't come from nowhere. It's not borrowed from the surrounding space or from some external source. It comes from the black hole's mass, ERMC2 in action. Every photon that escapes as Hawking radiation carries away a tiny bit of the black hole's mass energy. The event horizon shrinks slightly. The black hole becomes infinitesimally lighter. In a sense, the black hole is sacrificing itself, bit by bit, returning its mass to the universe over incomprehensible timescales. It's a slow reversal of the violent collapse that created it. What was compressed into a singularity is gradually being released back into space as radiation. There's something almost poetic about this. A cosmic recycling program operating on timescales far beyond anything biological or even stellar. And it raises deep questions about the nature of information and entropy. If a black hole eventually evaporates completely, what happens to all the information about the particles that fell in? Does it somehow escape in the Hawking radiation, encoded in subtle correlations we can't yet detect? Or is it truly lost, violating quantum mechanics? This is the information paradox we'll return to later, one of the deepest puzzles in theoretical physics. Material falling into a black hole first forms an accretion disk, a swirling, superheated disk of matter spiraling inward. When matter approaches a black hole, it rarely falls straight in. More often, it has some sideways motion, some angular momentum. This causes it to go into orbit, just like planets orbit stars. But unlike stable planetary orbits, these orbits decay over time due to friction and drag from other particles. The material forms a disk, a swirling structure called an accretion disk, with matter gradually spiraling inward toward the event horizon. As material in the accretion disk spirals inward, different parts move at different speeds. The inner regions orbit faster than the outer regions, and this differential motion creates friction. Particles rub against each other, generating enormous heat. The temperature in an accretion disk can reach millions or even billions of degrees, far hotter than the surface of any star. At these temperatures, the disk glows brilliantly, emitting visible light, ultraviolet light, X-rays, even gamma rays. This is the paradox of black holes. The black hole itself is invisible, emitting nothing, but the material falling toward it can be among the brightest objects in the universe. The accretion disk turns gravitational potential energy into heat and light with remarkable efficiency. In fact, accretion onto a black hole is one of the most efficient energy generation processes in nature, converting up to 10% or more of the infalling mass into radiated energy. That's far more efficient than nuclear fusion, which converts less than 1% of mass to energy. Not all material in an accretion disk falls in. Some is ejected in powerful jets shooting out from near the black hole's poles. Here's something that seems counterintuitive. Black holes? objects from which nothing can escape, can launch some of the most powerful jets in the universe. These jets shoot out perpendicular to the accretion disk from regions near the black hole's poles, carrying matter and energy away at speeds approaching the speed of light. Some jets extend for thousands or even millions of light years into space. The mechanism that creates these jets is complex and involves the black hole's rotation and powerful magnetic fields in the accretion disk. As the disk rotates, it can twist and amplify magnetic field lines, creating structures that channel some of the infalling material away from the black hole before it crosses the event horizon. Think of it like water spiraling down a drain. Most of it goes down, but splashes and sprays can escape before they reach the drain itself. These jets are incredibly energetic. They plow through intergalactic space, creating giant lobes of radio emission as they collide with tenuous gas far from the black hole. They can affect the evolution of entire galaxies, heating gas that might otherwise cool and form stars. In a sense, black holes can regulate their own food supply. By launching jets that heat and disperse nearby gas, they reduce the amount of material available to fall in. It's a form of cosmic feedback that connects the smallest scales, the event horizon, to the largest, galaxy evolution. Black hole jets are among the most energetic phenomena in the universe, powered by the black hole's rotation and magnetic fields. The power source for these jets is ultimately the black hole's rotation. A spinning black hole drags space-time around with it, and this rotational energy can be tapped. Magnetic fields threading through the accretion disk and anchored in the rotating space-time can extract this energy and channel it into the jets. It's a bit like a cosmic dynamo, converting rotational energy into the kinetic energy of particles shooting away at relativistic speeds. The particles in these jets are accelerated to incredible velocities. We're talking about electrons, protons, and heavier ions moving at 95%, 99%, even 99.9% the speed of light. At these speeds, relativistic effects become extreme. Time dilation, length contraction, enormous increases in effective mass. All the strange predictions of special relativity come into play. The jets glow with synchrotron radiation as charged particles spiral around magnetic field lines, creating the radio emissions we can detect with telescopes. What's remarkable is that this process can continue for millions of years. A supermassive black hole can maintain jets continuously, fed by a steady supply of infalling matter, powered by its rotation. These jets can carve out enormous cavities in the intergalactic medium, creating structures visible in X-ray and radio observations. They're rivers of energy flowing through the cosmos, connecting the immediate vicinity of the black hole to regions millions of light years away. A black hole's accretion disk can be as hot as hundreds of millions of degrees, hot enough to emit X-rays and gamma rays. At hundreds of millions of degrees, matter exists in a state utterly alien to our everyday experience. Atoms are completely ionized, electrons stripped away, leaving bare nuclei. The material is a fully ionized plasma, a sea of charged particles moving at tremendous speeds. At these temperatures, the peak emission is in X-rays and gamma rays, the highest energy forms of electromagnetic radiation. This is why we often detect black holes through X-ray telescopes rather than optical ones. The accretion disk is so hot it's essentially invisible to our eyes. Its peak emission is at wavelengths far shorter than visible light. But in X-rays, it blazes brilliantly. Some of the first black hole candidates were discovered as bright X-ray sources in the sky, mysterious points of intense high-energy radiation that could only be explained by matter falling into a compact, massive object. The temperature of the accretion disk isn't uniform. It's hottest in the inner regions, close to the event horizon, where the orbital speeds are highest and the gravitational energy release is most intense. Farther out, the disk is cooler, perhaps emitting invisible light or even infrared. This temperature gradient creates a spectrum, a range of wavelengths emitted, that astronomers can study to understand the physics of the disk and measure properties of the black hole itself. The material in an accretion disk orbits at different speeds depending on distance, creating friction that heats it to extreme temperatures. This differential rotation is key to understanding why accretion disks get so hot. In the inner regions of the disk, material orbits incredibly fast, a significant fraction of the speed of light for material close to a stellar mass black hole. Farther out, the orbital speed is slower, following Kepler's laws just like planets around a star. But unlike planets, which orbit in vacuum, the material in an accretion disk is constantly interacting with neighboring material. Imagine two streams of gas, one moving faster than the other, sliding past each other. They rub, they drag, they create friction. This friction converts the kinetic energy of orbital motion into heat. The faster the differential, the greater the speed difference between adjacent regions, the more heat is generated. Near a black hole, where orbital speeds change dramatically over short distances, this frictional heating becomes extreme. The result is a disk that's tremendously hot and bright, gradually transporting angular momentum outward while allowing matter to spiral inward. It's a delicate balance maintained by the complex interplay of gravity, pressure, magnetic fields, and radiation. And all of this happens in the immediate vicinity of an object from which light cannot escape, making the region around a black hole one of the most violent and energetic environments in the cosmos. Time slows down near a black hole, a phenomenon called gravitational time dilation. Time, we like to think, is constant. A second is a second, an hour is an hour, no matter where you are. But Einstein showed us this isn't true. Time is relative, affected by gravity and motion. Near a black hole, where gravity is extraordinarily strong, time slows down dramatically compared to regions farther away. This is gravitational time dilation, and it's not a subtle effect. It's profound and measurable. Imagine two people, one orbiting close to a black hole and one far away, in relatively flat space-time. The person close to the black hole experiences time normally from their own perspective. Their heartbeat feels regular. Their thoughts proceed at a normal pace. But to the distant observer, watching through a telescope, the person near the black hole appears to move in slow motion. Their clock ticks more slowly. They age more slowly. What feels like an hour to them might be days or weeks or years to the distant observer, depending on how close they are to the event horizon. This isn't science fiction or metaphor. It's a real physical effect that's been measured countless times. GPS satellites have to account for time dilation. Their clocks run slightly faster than clocks on Earth's surface because they're in a weaker gravitational field. Near a black hole, the effect is magnified enormously. Time itself becomes a variable, stretching and compressing depending on your position in the gravitational field. It's one of the ways black holes warp not just space, but space-time, the unified fabric of reality itself. At the event horizon itself, time essentially stops from an outside observer's perspective. This is perhaps the strangest consequence of time dilation. As you watch someone fall toward a black hole, you see them slow down as they approach the event horizon. Their movements become more and more sluggish. They appear to freeze, suspended just above the horizon, never quite crossing it. Their image fades, redshifted toward invisibility, but from your perspective, they never actually fall in. Time at the horizon, relative to your distant vantage point, has stopped. This creates a peculiar situation. From the outside, you never see anything cross the event horizon. The entire history of the black hole, all the matter that's ever fallen in, appears frozen at the surface in various stages of infinite redshift. It's like a museum of everything the black hole has ever consumed, preserved in eternal slow motion, though dimmed beyond visibility. But this is only from the outside perspective, and it raises a question we'll answer in the next fact. What about the perspective of the person falling in? Do they experience this freezing of time? The answer is both simple and profound, highlighting just how deeply relative our experience of reality can be near these extreme objects. But from the perspective of something falling in, crossing the event horizon happens in finite time. Here's where relativity shows its full strangeness. While the distant observer never sees you cross the horizon, you falling inward experience something completely different. From your perspective, time proceeds normally. You don't freeze. You don't slow down. You fall across the event horizon in a perfectly finite amount of time, seconds, minutes, or hours, depending on the black hole's mass and your trajectory. In fact, you might not even notice the moment you cross the horizon, especially for a supermassive black hole, where tidal forces at the horizon are gentle. You'd look around and see space continuing, perhaps strangely distorted by the extreme curvature, but continuous. Behind you, the universe outside would appear increasingly blue-shifted and bright as light from all of cosmic history appears to compress into your final moments. Ahead of you, darkness. This is the true meaning of relativity. Both perspectives are equally valid. The distant observer is correct that by their clock you never cross. You are correct that by your clock you do cross. There's no universal now that resolves this paradox. Time itself is fundamentally observer-dependent, and near a black hole, this dependence becomes impossible to ignore. You and the distant observer inhabit different temporal realities, each experiencing a valid but incompatible version of events. Light itself can orbit a black hole at a distance called the photon sphere, just outside the event horizon. At a specific distance from a black hole, 1.5 times the Schwarzschild radius for a non-rotating black hole, something extraordinary happens. The curvature of space-time is so extreme that light can travel in circular orbits, not spiraling in, not escaping out, but circling endlessly, locked in an orbital dance around the black hole. This region is called the photon sphere. These aren't stable orbits in any practical sense. They're perfectly balanced on a knife's edge. The slightest perturbation, a tiny gravitational tug from a passing particle, even the quantum uncertainty inherent in the photon's position, and the photon either falls into the black hole or escapes to infinity. But mathematically, theoretically, there exist these perfect circular paths where light can orbit forever. The photon sphere is one of the features visible in the famous image of the M87 black hole. Some of the light in that bright ring comes from photons that have orbited the black hole one or more times before escaping. They've traced out circles in the warped space-time, adding to the complex pattern of light we observe. It's a reminder that near a black hole, even light, which always travels in straight lines through flat space-time, must follow the curves imposed by extreme gravity. If you could somehow orbit at the photon sphere, you could theoretically see the back of your own head. This is one of those thought experiments that seems like it should be impossible but follows directly from the physics. At the photon sphere, light orbits the black hole. If you were somehow stationed there, held in place by some impossibly powerful rocket, since the orbit is unstable, light from the back of your head could travel around the black hole and arrive at your eyes from the front. You'd see multiple images of yourself actually. Light could orbit once, twice, 3 times before reaching your eyes. Each orbit would create a fainter, more distorted image wrapped around the black hole in increasingly tight circles. It would be like standing in a hall of mirrors, except the mirrors are space-time itself, curved into loops by gravity. Of course, this is purely theoretical. Nothing material could maintain a stable position at the photon sphere. The orbit is inherently unstable, and you'd need infinite thrust to stay there. And even if you could, the tidal forces might be uncomfortable or lethal, depending on the black hole's mass. But as a thought experiment, it beautifully illustrates how profoundly black holes warp the paths that light takes through space, creating geometries that seem to belong more to mathematics than to physical reality. Rotating black holes drag space-time around with them in a phenomenon called frame dragging. A non-rotating black hole just sits there, warping space-time around it. But most black holes rotate. They were formed from rotating stars or grew by accreting matter with angular momentum. And a rotating black hole does something even stranger. It drags space-time along with it. This is frame dragging, sometimes called the lens-thirring effect, and it's a prediction of general relativity that's been confirmed by experiments near Earth and inferred around black holes. Imagine space-time as a viscous fluid, like honey. When the black hole spins, it stirs this fluid, creating a swirling pattern. Near the black hole, space-time itself is rotating, pulled along by the black hole's angular momentum. This isn't just a metaphor, it's what's actually happening. The reference frames, the coordinate systems you'd use to measure position and time, are being dragged in the direction of the black hole's rotation. This has profound effects. An object near a rotating black hole experiences forces not present near a non-rotating one. Orbits precess. They shift gradually in the direction of rotation. Light paths curve differently. The entire geometry of space-time is twisted, no longer symmetric, creating a dynamic, rotating structure that extends outward from the event horizon. It's as if the black hole has imprinted its rotation onto the fabric of reality itself. The region where frame dragging becomes unavoidable is called the ergosphere. Outside the event horizon of a rotating black hole, there's another boundary called the ergosphere. It's a region where the dragging of space-time becomes so extreme that nothing can remain stationary, not even with infinite thrust. Space itself is moving, and you must move with it, rotating in the same direction as the black hole, whether you like it or not. The ergosphere extends farther from the poles of the black hole and meets the event horizon at the equator. Within this region, you can still escape. You haven't crossed the event horizon, but you can't stand still. All trajectories, even those of light, must have some component of motion in the direction of the black hole's rotation. It's like being caught in a cosmic whirlpool. You can swim outward and escape, but you can't stop rotating with the current. What makes the ergosphere particularly interesting is that it's theoretically possible to extract energy from it through the Penrose process, which we'll discuss soon. The rotational energy of the black hole is, in a sense, accessible from the ergosphere, in a way it isn't from outside. This makes rotating black holes not just more complex than non-rotating ones, but fundamentally different in their interaction with the surrounding universe. Some black holes spin at nearly the speed of light, rotating hundreds of times per second. The fastest spinning black holes we've detected are rotating at truly staggering rates. For a stellar mass black hole, this might mean hundreds of complete rotations per second. For a supermassive black hole, which is much larger, even a rotation every few minutes represents a surface velocity near the speed of light. These are objects with the mass of millions or billions of suns, spinning fast enough that their equators are moving at relativistic speeds. This extreme rotation warps space-time dramatically. The ergosphere is larger and more pronounced. Frame dragging effects extend farther into space. The innermost stable orbit, the closest distance at which matter can orbit before falling in, moves closer to the event horizon for a spinning black hole than a non-spinning one, allowing matter to orbit in regions of even more extreme gravity and curvature. How do black holes spin up to these speeds? They accrete matter with angular momentum, and each addition of mass carries rotational energy. Over time, as the black hole consumes gas and stars and other black holes, it can accumulate tremendous angular momentum. There's likely a maximum spin rate, near the theoretical limit where the event horizon would disappear. But many black holes appear to be spinning close to this limit, rotating as fast as the laws of physics allow. It's theoretically possible to extract energy from a rotating black hole through a process called the Penrose process. In 1969, physicist Roger Penrose described a remarkable possibility. If you send a particle into the ergosphere of a rotating black hole and arrange for it to split into two particles, with one falling into the black hole and one escaping, the escaping particle can carry away more energy than the original particle had. Where does this extra energy come from? From the rotational energy of the black hole itself. The black hole spins slightly slower after the process, and that lost rotational energy appears as increased energy in the escaping particle. This is, In principle, a way to extract usable energy from a black hole. An advanced civilization might surround a spinning black hole with machinery designed to repeatedly perform the Penrose process, harvesting rotational energy without needing to cross the event horizon. The black hole would gradually slow down, its spin decreasing over time, but enormous amounts of energy could be extracted in the process. No one's building a Penrose process power plant anytime soon. The engineering challenges are absurd, even by science fiction standards. But the theoretical possibility is fascinating. It suggests that black holes, far from being just cosmic dead ends, could potentially serve as energy sources. They're batteries, in a sense, storing rotational energy that could theoretically be tapped. It's a reminder that even the strangest objects in the universe might someday have practical applications we can barely imagine now. Black holes are the most efficient gravitational batteries in the universe. Up to 42% of an object's mass can theoretically be extracted as energy. Here's a remarkable number. If you drop matter into a maximally spinning black hole, allowing it to orbit as close to the event horizon as possible before falling in, you can extract up to 42% of that matter's rest mass as energy. Compare that to nuclear fusion, humanity's most powerful energy source, which converts less than 1% of mass to energy. Black hole accretion is orders of magnitude more efficient. This efficiency comes from the extreme depths of the gravitational potential well. As matter falls toward the black hole, it loses gravitational potential energy, which gets converted into kinetic energy, and then, through friction in the accretion disk, into heat and radiation. The closer the matter can get before falling in, the more energy can be extracted. For maximally spinning black holes, the innermost stable orbit is very close to the event horizon, allowing matter to release a tremendous fraction of its mass energy before disappearing. This is why quasars can be so luminous. A supermassive black hole accreting matter at even modest rates can outshine hundreds of billions of stars. The black hole is converting infalling matter into energy with extraordinary efficiency, powering some of the brightest phenomena in the universe. In a sense, black holes are nature's most effective engines for converting mass into light, operating at efficiencies that make our best technologies seem primitive by comparison. If you fell into a supermassive black hole feet first, you'd have minutes to hours before reaching the singularity. This is one of the more unsettling thought experiments in astrophysics. For a supermassive black hole, the kind at the center of galaxies, the event horizon is enormous, perhaps millions of kilometers across. Once you cross it, you're cut off from the outside universe completely. No signal you send can escape. No rescue is possible. You're in a region of space-time that's disconnected from everything you've ever known. And yet, you're still alive, still conscious, still experiencing time. From your perspective, you continue falling. The tidal forces at the horizon of a supermassive black hole are gentle enough that you remain intact. You have time to think, to observe, to contemplate what's happening. Minutes pass, perhaps hours, depending on the black hole's mass and your trajectory. During this time, you're in a kind of cosmic limbo, still existing, still experiencing reality, but forever separated from the rest of the universe. What would you see during this fall? Looking outward toward the universe you left behind, you'd see strange distortions. Light from the outside would be blue shifted, compressed, perhaps showing you the entire future history of the universe playing out in accelerated time. Looking inward toward the singularity, there would be only darkness ahead, the unknown center where space-time itself breaks down. You'd have this strange, final journey, isolated, doomed, but with time to reflect on the extraordinary circumstance you find yourself in. Light emitted from near a black hole's event horizon becomes severely redshifted, losing energy as it climbs out of the gravity well. Imagine a photon being emitted from deep in a black hole's gravitational field, near but outside the event horizon. To escape to a distant observer, it has to climb out of an enormous gravitational well, and climbing costs energy. The photon doesn't slow down. Light always travels at the speed of light, but it loses energy in another way. Its wavelength stretches, shifting toward the red end of the spectrum. This is gravitational redshift. A photon emitted as high-energy gamma radiation near the event horizon might arrive at a distant telescope as a low-energy radio wave, having lost most of its energy to the climb out of the gravitational field. The closer to the event horizon the emission occurs, the more severe the redshift. Right at the horizon, the redshift becomes infinite, which is another way of understanding why light can't escape from the horizon itself. This gravitational redshift is one of the key observational signatures of black holes. When we observe hot gas near a black hole, we're not seeing it at its true temperature or energy. We're seeing a red-shifted, dimmed version. The actual emissions near the event horizon are far more energetic than what reaches our telescopes. Astronomers have to account for this effect when studying black hole accretion disks, correcting for the energy lost as light climbs out of the gravitational well. Around a spinning black hole, there are stable orbits closer to the horizon than around a non-spinning one. The rotation of a black hole changes its geometry in ways that affect orbits. For a non-rotating black hole, there's a limit to how close you can orbit stably, the innermost stable circular orbit, or ISCO. Inside this radius, no stable orbit exists. You might manage a few loops before spiraling in, but you can't maintain a circular orbit indefinitely. For a non-rotating black hole, this limit is at 3 times the Schwarzschild radius. But for a maximally spinning black hole, something remarkable happens. If you orbit in the same direction as the black hole's rotation, prograde orbits, the innermost stable orbit moves closer to the event horizon. It can get as close as about 1.23 times the event horizon radius for a maximally spinning black hole. Frame dragging helps stabilize the orbit, allowing matter to orbit in regions where it couldn't around a non-rotating black hole. This has profound implications for accretion. Matter orbiting closer to the event horizon can release more gravitational potential energy before falling in, making rapidly spinning black holes more efficient at converting mass to energy. It also affects what we see in observations. The inner edge of the accretion disk is closer to the black hole for rapidly spinning ones, creating different spectral signatures that allow astronomers to measure black hole spin from millions of light years away. Black holes can act as gravitational lenses, bending light from background objects and creating multiple distorted images. General relativity predicts that mass curves space-time, and this curvature affects the paths that light takes. We see this effect throughout the universe, galaxies bending light from more distant galaxies behind them, creating arcs and multiple images. Black holes, being extremely compact and massive, create particularly strong gravitational lensing. Light from a star or galaxy behind a black hole can take multiple paths around the black hole to reach us. Some light might pass on the left, some on the right. Some might even orbit the black hole once or multiple times before escaping. Each path creates a separate image. The result is a complex pattern, possibly a ring-like structure, multiple distorted images, or an Einstein ring if the alignment is perfect. This lensing is strongest for light passing very close to the black hole, near the photon sphere. The black hole acts like a cosmic magnifying glass, though one that distorts rather than clarifies. Observing these lensing effects can tell us about the black hole's mass and spin. In some cases, astronomers have used gravitational lensing by black holes to study objects that would otherwise be too faint to see, borrowing the black hole's gravity as a natural telescope. The shadow of a black hole is about 2.5 times larger than the event horizon itself. When we talk about the shadow of a black hole, we mean the dark region that appears in images like the one from M87. This shadow isn't just the event horizon, it's larger, encompassing not only the horizon, but also a region around it where light gets captured. Light that passes too close to the black hole, even if it starts outside the horizon, can be bent around and captured, never escaping to reach our telescopes. The exact size of the shadow depends on the black hole's spin and our viewing angle, but for a non-rotating black hole, it's about 2.5 times the Schwarzschild radius. This factor comes from the bending of light paths in the curved space-time around the black hole. Photons that would naively seem to pass by at a safe distance actually get pulled in, enlarging the apparent dark region. This is why the M87 image is so valuable scientifically. The size and shape of the shadow encode information about the black hole's mass and spin. By measuring these properties carefully and comparing them to theoretical predictions, astronomers can test general relativity in one of its most extreme regimes. The fact that the observed shadow matches Einstein's predictions so precisely is a triumph for our understanding of gravity and space-time. Gas falling into a black hole can complete several orbits before crossing the horizon, radiating away energy and momentum. Material doesn't just plunge straight into a black hole. As we've discussed, it forms an accretion disk and spirals gradually inward. During this inward spiral, the gas can orbit many times, dozens, hundreds, perhaps even thousands of times, depending on the disk's properties and the efficiency of angular momentum transport. Each orbit carries the material slightly closer to the event horizon as friction and magnetic fields remove angular momentum. During these orbits, the gas radiates energy as heat and light. It's a gradual process, a slow descent rather than a sudden plunge. The gas heats up, glows more brightly, orbits faster and faster as it gets closer, emitting more and more energetic radiation. This gradual infall creates the characteristic spectrum we observe from accreting black holes, a broad continuum of radiation spanning many wavelengths, from radio waves to X-rays, or even gamma rays, depending on the temperature achieved. The spectrum contains information about the disk's temperature profile, the rate of accretion, and the black hole's properties. Astronomers decode this light to understand the physics of matter in these extreme environments. At the innermost stable circular orbit, material must either fall in or be ejected. There are no stable orbits closer to a black hole. The innermost stable circular orbit, or ISCO, is a critical boundary in black hole physics. Outside this radius, circular orbits are stable. Material can orbit indefinitely if undisturbed. But inside it, there are no stable circular orbits. Material might manage elliptical orbits or temporary circular ones, but they're unstable. The slightest perturbation sends the material either crashing inward toward the event horizon or potentially being flung outward. For a non-rotating black hole, the ISCO is at 3 Schwarzschild radii, or about 6 times the horizon radius. This is where the innermost edge of the accretion disk typically forms. Material reaches this point, releases its remaining orbital energy in one final burst of radiation, and then plunges inward. The journey from the ISCO to the event horizon happens quickly. There's no gradual spiral anymore, just a rapid fall. The ISCO is like a last rest stop before the final plunge. It's the point where orbital mechanics gives way to inevitable infall. Beyond this boundary, the black hole's gravity is so strong and the curvature so extreme that stable circular motion becomes impossible. Material has one last moment in stable orbit, then crosses a threshold beyond which there's no more delay, only the journey to the event horizon and beyond. The gravity near a stellar mass black hole is so intense that tidal forces would rip apart any known material before it crossed the horizon. For smaller black holes, those formed from stellar collapse, with masses from a few to perhaps 100 times the Sun's mass, the event horizon is compact, just kilometers or tens of kilometers across, and the tidal forces near such a compact horizon are enormous, far exceeding anything we've discussed about spaghettification. Any material object, a spacecraft, a human body, even an atomic nucleus held together by the strong force, would be torn apart by tidal forces before reaching the event horizon. The difference in gravitational pull across even small distances becomes so extreme that molecular bonds, atomic forces, even nuclear forces can't withstand it. You'd be ripped into a stream of subatomic particles, a beam of matter falling into the black hole, only for supermassive black holes, with their enormous event horizons and correspondingly gentler tidal forces at the horizon. Could you potentially survive crossing intact? For stellar mass black holes, the horizon itself is a region of such extreme tidal stress that nothing structured can survive there. It's an ultimate limit imposed by the black hole's compactness. The same property that allows it to exist also makes its immediate vicinity utterly destructive to any material complexity. Black holes are perfect absorbers. Anything that crosses the horizon is gone from our universe's perspective, absorbed completely. In physics, we often talk about black bodies, idealized objects that absorb all electromagnetic radiation that hits them, reflecting nothing. Real materials approximate this behavior to varying degrees, but a black hole is the ultimate black body. It has an absorption coefficient of exactly 1.0 for anything crossing the event horizon. Perfect, total absorption. Matter, energy, information. Whatever crosses the horizon is absorbed. There's no reflection, no scattering, no bouncing back. The event horizon is a one-way membrane, and unlike material absorbers, which can be saturated or damaged by absorbing too much, a black hole simply grows. Each absorption adds to its mass, expands its event horizon slightly, and makes it capable of absorbing even more. This perfect absorption is another aspect of the information paradox. Quantum mechanics says information should be conserved. The universe should maintain a complete record of all quantum states. But black holes seem to delete information, absorbing it completely and irretrievably. Hawking radiation might carry information out, encoded in subtle correlations, but we don't yet know how. The perfect absorption of black holes creates one of the deepest puzzles at the intersection of quantum mechanics and gravity. Despite their extreme nature, black holes obey the same conservation laws as everything else. They conserve energy, momentum, and angular momentum. It might seem like black holes break all the rules, but they don't break the fundamental conservation laws of physics. When mass falls into a black hole, the total energy of the system is conserved. It's just that some of it is now inside the event horizon, inaccessible to the outside universe. When a black hole moves, it carries momentum. When it spins, it has angular momentum. These quantities are conserved in all interactions. When two black holes merge, the final black hole has the mass, momentum, and angular momentum of the two original holes, minus whatever was carried away as gravitational waves. Conservation laws hold precisely. The same is true for electric charge, though as we've discussed, most black holes are probably electrically neutral. This is reassuring in a way. Black holes are strange, extreme, seemingly alien objects, but they're not magic. They're not violations of physics. They're solutions to Einstein's equations, subject to the same fundamental principles that govern everything else in the universe. They conserve what must be conserved. They follow deterministic evolution. They interact with their environment according to well-defined rules. Strange they may be, but lawless they are not. They remind us that even at the extremes, the universe maintains its internal consistency. In 2015, humanity detected gravitational waves from merging black holes for the first time, confirming a century-old prediction. On September 14, 2015, at 09:50:45 UTC, two detectors in the United States, one in Louisiana, one in Washington state, registered a signal that had traveled across 1.3 billion light-years of space. It lasted less than a second, a characteristic chirp rising in frequency and amplitude before fading away. This was the sound, translated into audio frequencies, of two black holes spiraling together and merging, an event that happened when Earth was populated by simple multicellular organisms. This detection confirmed something Einstein had predicted in 1916, but doubted would ever be observed: gravitational waves, ripples in the fabric of space-time itself. The merger released more power in gravitational waves than all the stars in the observable universe combined were emitting in light at that moment. And yet, by the time those waves reached Earth, they were so weak they changed the lengths of the LIGO detectors by less than 1,000th the width of a proton. The achievement was extraordinary on multiple levels. It confirmed general relativity's predictions in the strongest gravitational fields we can observe. It opened an entirely new way of observing the universe, not through electromagnetic radiation, but through the vibrations of space-time itself. And it proved that black hole mergers actually happen, giving us direct evidence of these cosmic collisions. It was a moment when theoretical prediction, century-old mathematics, and cutting-edge experimental physics all aligned perfectly. Gravitational wave detectors can hear black hole mergers happening billions of light years away. The technology required to detect gravitational waves borders on the miraculous. LIGO, the Laser Interferometer. Gravitational Wave Observatory uses laser beams traveling along arms 4 kilometers long. When a gravitational wave passes through, it stretches space in one direction while compressing it in the perpendicular direction. The lasers measure these changes with extraordinary precision, detecting distortions smaller than a proton across distances of kilometers. Since that first detection in 2015, gravitational wave observatories have detected dozens of black hole mergers, along with neutron star mergers and other events. Some of these happened billions of light years away, when the universe was less than half its current age. We're hearing collisions that occurred in the distant past, the gravitational echoes of violence that shape the cosmic structure we see today. What's remarkable is how much information is encoded in these signals. The frequency and amplitude of the waves tell us the masses and spins of the merging black holes. The rate at which the frequency increases tells us how quickly they're spiraling together. The final ring down, the damped oscillations after the merger, reveals the properties of the final black hole. From a signal lasting less than a second, we can reconstruct the entire story of two black holes' final dance. We've now detected dozens of black hole mergers through gravitational waves, revealing a population we never knew existed. Before gravitational wave astronomy, we knew about stellar mass black holes primarily through X-ray binary systems. Black holes with companion stars, pulling matter from them and glowing brightly in X-rays. These ranged from a few to perhaps 20 solar masses. But gravitational wave detections have revealed black holes significantly more massive, ranging up to 50, 60, even 70 solar masses or more in some cases. This was surprising. Stellar evolution models suggested it would be difficult to form such massive black holes through normal stellar collapse, at least in environments with the metallicity of nearby galaxies. Yet here they are, merging in large numbers, suggesting that either our understanding of stellar evolution needs refinement, or these black holes form through different mechanisms, perhaps through multiple mergers, building up mass over time. Each detection adds to a growing catalog of black hole properties, masses, spins, merger rates. We're building a census of the black hole population in the universe, learning about how they form, how they evolve, how often they merge. It's like discovering an entire ecosystem that was invisible to previous methods of observation. Gravitational wave astronomy has, in just a few years, revolutionized our understanding of black holes and their role in cosmic evolution. In 2020, we imaged our own galaxy's supermassive black hole, Sagittarius A. for the first time. After the success of imaging M87's black hole in 2019, the Event Horizon Telescope team turned their attention to a closer, more challenging target: the supermassive black hole at the center of our own Milky Way galaxy. Sagittarius A is much closer than M87's black hole, only about 26,000 light-years away compared to 55 million. But it presented unique difficulties. The problem is variability. Material orbiting Sagittarius A completes an orbit in minutes to hours, compared to days or weeks for M87. This means the appearance of the accretion disk changes rapidly. It's like trying to photograph a fidgety child versus a patient adult. The data from different telescopes has to be carefully synchronized and processed to account for these rapid changes. Nevertheless, in 2022, the team revealed the image: another bright ring surrounding a dark shadow, this time of our own galaxy's central black hole. The image confirmed that Sagittarius A has the properties we expected from decades of studying stellar orbits around it. It also provided another test of general relativity, showing that Einstein's predictions hold even for the black hole at the heart of our home galaxy. We had finally seen both an incredibly distant, supermassive black hole and our own, confirming that these objects exist throughout the universe. Some black holes are feeding so vigorously they create quasars, among the brightest objects in the universe. Quasars are among the most luminous phenomena in the cosmos. A single quasar can outshine all the hundreds of billions of stars in its host galaxy combined. And at the heart of each quasar is a supermassive black hole consuming matter at a tremendous rate, sometimes hundreds or even thousands of solar masses per year, though the average is probably closer to a few solar masses annually. As this matter spirals into the black hole through an accretion disk, it heats to billions of degrees and radiates across the electromagnetic spectrum. The disk glows brilliantly in visible light, ultraviolet, and X-rays. Jets launched from near the black hole can extend for hundreds of thousands or millions of light years, creating enormous radio lobes. The entire system becomes a beacon, visible across the universe. Quasars were more common in the early universe when galaxies were forming and merging more frequently, providing abundant fuel for central black holes. Today, most supermassive black holes, including our own Sagittarius A, are relatively quiet. They're not consuming much material and shine only faintly. But in rare cases where a black hole has access to large amounts of gas, perhaps from a galaxy collision, it can briefly reignite as a quasar, blazing across the cosmos once again. We've discovered black holes forming earlier in cosmic history than our models predicted possible. When astronomers look at the most distant quasars, those existing less than 1 billion years after the Big Bang, they find supermassive black holes that are already billions of times the Sun's mass. This timeline seems impossibly tight. Even if you started with a stellar mass black hole formed from one of the universe's first stars and had it feed at the maximum possible rate continuously, it shouldn't have time to grow this large, this quickly. This early existence of supermassive black holes is one of the puzzles driving current research. Maybe these black holes didn't start from stellar mass seeds. Maybe they formed from the direct collapse of massive gas clouds in the early universe. starting with masses of thousands or even millions of suns. Or maybe there were mechanisms in the early universe that allowed faster growth than we currently understand. New observations from powerful telescopes, like the James Webb Space Telescope, are finding even more of these early quasars, pushing the timeline back further. Each discovery refines our understanding and constrains the possible formation mechanisms. It's a reminder that the early universe was a different place, with conditions and processes that don't have perfect analogs in the cosmos today. Those first billion years held events we're still trying to understand. Recent observations suggest some supermassive black holes might have formed directly from collapsing clouds of gas, skipping the star stage entirely. The direct collapse scenario is an elegant solution to the early black hole problem. In the very early universe, before much star formation had occurred, there existed clouds of primordial gas, hydrogen and helium mostly, with very few heavier elements. Under the right conditions, these clouds could collapse directly into black holes without fragmenting to form stars first. This would require specific circumstances. The gas would need to be unusually hot, preventing it from cooling and fragmenting into smaller clumps. There might need to be intense radiation from nearby sources, keeping the gas ionized. But if conditions aligned, a cloud containing tens of thousands or hundreds of thousands of solar masses could collapse directly into a black hole of similar mass. These seeds would have a major head start compared to stellar mass black holes. Evidence for direct collapse is circumstantial. So far, we haven't directly observed it happening, but the mere existence of billion solar mass black holes less than a billion years after the Big Bang argues that something like this must have occurred. The universe found a way to make supermassive black holes quickly, and direct collapse is one of the more plausible mechanisms. It suggests the universe's first black holes might have been very different from the ones forming today, from dying stars. Stars can orbit extremely close to Sagittarius A, some completing an orbit in just 16 years, despite being light years from the black hole. The star S2, which we've mentioned before, has an elliptical orbit that brings it to within about 17 light hours of Sagittarius A, roughly 120 astronomical units, or about 4 times the distance from the Sun to Neptune. At this distance, traveling at about 3% of the speed of light at closest approach, S2 completes a full orbit in 16 years. Astronomers have now tracked S2 through multiple complete orbits, creating one of the most precise measurements of a black hole's properties ever made. They've observed the star's orbit precess shift slightly with each passage, just as Einstein's general relativity predicts. They've measured the gravitational redshift of light from the star as it climbs out of the black hole's gravity well. They've even detected relativistic effects in the star's apparent position. There are even closer stars. S62, discovered more recently, has an orbital period of just 9.9 years and approaches even closer to the black hole. These stars are laboratories for testing physics in extreme conditions. They experience gravitational fields and velocities that would be impossible to study anywhere else. Each orbit provides another opportunity to test general relativity, to measure the black hole's mass and spin more precisely, and to search for deviations from Einstein's predictions that might hint at new physics. By tracking stars orbiting our galaxy's central black hole, we've measured its mass with extraordinary precision. The mass of Sagittarius A is now known to be approximately 4.15 million solar masses, with an uncertainty of just a few percent. This precision comes from decades of patient observation, tracking the motions of dozens of stars in the central region, some for complete orbits, building up a detailed map of the gravitational field. This measurement is based on Kepler's laws, the same principles that govern planetary orbits around the Sun apply to stellar orbits around black holes. By measuring a star's orbital period and the size of its orbit, you can calculate the mass of the object it's orbiting. The more stars you track, the more orbits you observe, the more precise your measurement becomes. What makes this measurement extraordinary is the length of the baseline. Some of these observations span 25 years or more, requiring consistency in instrumentation, technique, and analysis across decades. Different research groups using different telescopes have independently arrived at consistent results. It's a testament to the precision of modern astronomy that we can measure the mass of an object 26,000 light-years away to within a few percent accuracy. Some black holes are moving through space at high speeds, sometimes kicked by asymmetric gravitational wave emission during mergers. When two black holes merge, if the collision isn't perfectly symmetric, if they have different masses or spins, or if they're not aligned, the gravitational waves are emitted preferentially in certain directions. This creates a rocket effect. The waves carry momentum, and conservation of momentum means the final black hole recoils in the opposite direction, like a gun kicking back when fired. These recoil velocities can be substantial, hundreds or even thousands of kilometers per second in extreme cases. That's fast enough for the black hole to be ejected from its host galaxy entirely, becoming a wandering black hole moving through intergalactic space. More modest kicks might displace the black hole from the galaxy's center, creating an off-center supermassive black hole that gradually sinks back toward the middle over millions of years. We found evidence for these recoiling black holes in observations of galaxies with off-center active nuclei, or with unusual kinematic signatures, suggesting the central black hole is moving relative to the surrounding stars. Each detection tells a story of a violent merger in the past, an asymmetric collision that launched the black hole on a new trajectory through space. They're cosmic evidence of the tremendous energies involved in black hole mergers. We've discovered that the relationship between a galaxy's central black hole and the galaxy itself is surprisingly tight. In the late 1990s and early 2000s, astronomers made a startling discovery when they measured the masses of supermassive black holes in various galaxies and compared them to properties of those galaxies. They found correlations, strong correlations. The black hole's mass seemed to be directly related to the mass of the galaxy's central bulge and to the velocity dispersion, the average speeds of stars in the central region. This relationship is surprisingly tight. The black hole typically contains about 0.1% to 0.2% of the bulge mass. Given that the black hole occupies a region millions of times smaller than the bulge, this correlation is remarkable. How does the black hole know about the mass of stars distributed over a much larger volume? How do structures at such different scales, the event horizon spanning light hours, the bulge spanning thousands of light years, become so precisely coordinated? The correlation suggests these components aren't evolving independently. The black hole and the galaxy must be influencing each other's growth throughout cosmic history. It's a coupling that wasn't predicted by early theories, but has become one of the key observational facts that theories of galaxy evolution must explain. Understanding this relationship is crucial to understanding how galaxies develop their structure over billions of years. This suggests black holes and galaxies grow together, each influencing the other's evolution over billions of years. The correlation between black hole mass and galaxy properties points to a process called coevolution. As a galaxy forms and grows through cosmic time, accreting gas and merging with other galaxies, its central black hole grows too. And crucially, the black hole's activity, its jets, its radiation, the energy it releases as it feeds, affects the galaxy's ability to form stars and continue growing. When a black hole is actively feeding, the energy it releases can heat gas throughout the galaxy, preventing it from cooling and collapsing to form new stars. This is called feedback, and it's thought to be a crucial regulator of galaxy growth. Without it, galaxies would convert too much of their gas into stars too quickly, creating galaxies much more massive than we actually observe. The black hole, despite being tiny compared to the galaxy, helps determine when and where stars can form. At the same time, the galaxy feeds the black hole. Galaxy mergers funnel gas toward the center, providing fuel for the black hole to consume. Supernova explosions and stellar winds blow gas around, some of it ending up in the central region. The galaxy creates the environment that determines how fast the black hole can grow. They're partners in a cosmic dance, each shaping the other, neither evolving in isolation. It's an intimate relationship between the very large and the very small. Black hole jets can actually suppress star formation in galaxies by heating and dispersing the gas that would form stars. This feedback mechanism works through the jets and winds launched by active black holes. When a supermassive black hole is feeding vigorously, it launches jets that plow through the surrounding gas. These jets transfer enormous amounts of energy to the gas, heating it and stirring it up. Hot, turbulent gas doesn't easily collapse to form stars. It's too energetic, too disrupted. Observations show this happening in real galaxies. Around some active black holes, astronomers see cavities in the surrounding gas, bubbles blown out by the jets. The gas in these regions is much hotter than it would be otherwise. Star formation is suppressed compared to similar galaxies without active central black holes. The black hole is quite literally preventing its host galaxy from forming new stars. This might seem destructive, but it's actually crucial for understanding why galaxies look the way they do. Without this feedback, the most massive galaxies would be much more massive. They'd have converted far more of their gas into stars. The black hole acts as a thermostat of sorts, regulating the galaxy's star formation and helping determine its final mass and structure. It's a form of self-regulation. The galaxy feeds the black hole grows, and its activity eventually reduces the galaxy's ability to continue feeding it. Some astronomers are searching for primordial black holes as potential dark matter candidates. Dark matter is one of cosmology's greatest mysteries. We know it exists because of its gravitational effects. Galaxies rotate too fast. Galaxy clusters hold together too strongly. Gravitational lensing is too strong for the visible matter alone to explain. Yet we've never directly detected dark matter particles. What if dark matter isn't exotic particles at all, but rather black holes? Primordial black holes? Those formed in the early universe rather than from stellar collapse, could exist across a wide range of masses, including masses where we wouldn't easily detect them. If the universe created enough of these small black holes in its first moments, they could make up some or all of the dark matter. They'd be invisible, they'd have mass. They'd clump gravitationally just like dark matter should. The idea has waxed and waned over the decades as various observations have constrained which mass ranges are viable. Certain mass ranges are ruled out. We'd see effects we don't observe if there were too many primordial black holes in those ranges. But there are still windows where primordial black holes could constitute a significant fraction of dark matter. Searches continue using gravitational lensing, gravitational waves, and other techniques to look for evidence of these ancient, invisible wanderers. Improved simulations now show us what happens when black holes merge, revealing details impossible to observe directly. General relativity is notoriously difficult to solve. Einstein's field equations are a set of 10 coupled, nonlinear partial differential equations. For simple, symmetric cases like a non-rotating black hole, exact solutions exist. But for two black holes spiraling together, merging and settling down, that requires numerical solutions, supercomputers solving the equations step by step, calculating how space-time curves and evolves. In the early 2000s, breakthroughs in numerical relativity finally allowed physicists to simulate black hole mergers from start to finish. These simulations run on some of the world's most powerful supercomputers, requiring months of computation time to simulate fractions of a second of real time. They divide space-time into a grid and calculate how each piece evolves, tracking the black holes in spiral, merger, and ring down. The results have been revelatory. Simulations predicted the gravitational wave signals we'd detect, allowing LIGO to know what to look for. They've shown how black holes spin and merge, how much energy gets radiated, how the final black hole settles into its equilibrium state. They've revealed that space-time during a merger develops complex dynamic structure, ripples and warps propagating outward. We can visualize what happens in regions of space-time we could never observe directly, watching the fabric of reality itself dance and merge. Every large galaxy appears to host a supermassive black hole at its center, suggesting they're fundamental to galaxy formation. This ubiquity is striking. It's not that some galaxies have central black holes, it's that essentially all large galaxies do. The Milky Way has one. Andromeda has one. Messier 87, Centaurus A, every large galaxy we've examined closely enough shows evidence of a supermassive black hole at its core. The masses vary, but the presence seems universal. This universality suggests that supermassive black holes aren't rare accidents or special cases. They're a fundamental component of galaxy structure, as natural and expected as the bulge or disk. Their formation must be a generic outcome of whatever processes create galaxies. Perhaps black holes form first, and galaxies assemble around them. Perhaps they form simultaneously, but one way or another, galaxies and supermassive black holes come as a package. There might be exceptions. Small dwarf galaxies might lack central black holes or have much smaller ones. But for galaxies of substantial mass, the pattern holds. It's a clue that galaxy formation and black hole formation are deeply connected processes. You apparently can't make one without the other, at least not in our universe with its particular laws of physics and initial conditions. When galaxies merge, their central black holes eventually merge too, creating even larger supermassive black holes. Galaxy mergers are common throughout cosmic history, especially in the earlier universe. When two galaxies collide, their stars mostly pass by each other. Space is mostly empty, after all. But their gas collides and shocks. Their gravitational fields stir each other up, and eventually they settle into a single, merged galaxy. And their central black holes? They sink toward the center of the new galaxy and eventually merge. This process takes time. First, the black holes have to spiral together through the merged galaxy, losing orbital energy to gravitational interactions with surrounding stars, a process called dynamical friction. Once they get close enough, they form a binary black hole orbiting each other. This binary shrinks through interactions with passing stars and emission of gravitational waves. Finally, when they're very close, separated by just astronomical units or less, gravitational waves dominate and they spiral together rapidly and merge. In a few billion years, when the Milky Way and Andromeda galaxies collide and merge, our black hole Sagittarius A will eventually merge with Andromeda's central black hole. The final merged black hole will be more massive than either predecessor, containing the accumulated mass of both. It will emit a powerful burst of gravitational waves as it forms. Waves that will propagate across the universe, carrying the story of two galaxies' long-delayed reunion. Black holes are among the most efficient engines in the universe for converting mass into energy. We've touched on this before, but it bears repeating because it's so remarkable. Drop matter into a spinning black hole, let it orbit in an accretion disk, and you can extract up to 42% of its rest mass as energy. This efficiency is unmatched by any other natural process. Nuclear fusion in stars converts less than 1% of mass to energy. Matter-antimatter annihilation achieves 100%, but antimatter is exceedingly rare in nature. Black hole accretion is so efficient because of the depth of the gravitational well and the ability of matter to orbit very close to the event horizon before falling in. Each orbit deeper in the well allows matter to release more gravitational potential energy. By the time material at the innermost stable orbit finally plunges in, it's already released a large fraction of its mass energy to the disk through friction and radiation. This efficiency explains why accreting black holes can be so luminous. Even modest accretion rates, a few solar masses per year, can power quasars that outshine hundreds of billions of stars. The black hole acts as an engine converting the latent energy of mass into radiation with extraordinary effectiveness. In a universe where energy efficiency often matters for astrophysical processes, black holes are among nature's best solutions for extracting energy from matter. The material spiraling into supermassive black holes can create enough radiation to outshine all the stars in the galaxy. Imagine all the stars in a galaxy, 100 billion suns, each radiating energy from nuclear fusion. And then imagine a single object at the galaxy's center outshining all of them combined. This is what happens in the brightest quasars and active galactic nuclei. The accretion disk around the central supermassive black hole, perhaps just light years across, produces more luminosity than all those stars spread across 100,000 light years. This radiation comes in all wavelengths. Visible light, certainly. Quasars often appear as bright point sources in optical images, but also ultraviolet radiation from the hottest parts of the disk, X-rays from gas very close to the event horizon, infrared from cooler outer regions, and dust heated by the central radiation. The entire electromagnetic spectrum carries energy away from the accretion process, and this is just from the material falling in. Add the jets, which can extend for hundreds of thousands of light years and emit powerful radio waves, and the total energy budget becomes staggering. A single actively feeding supermassive black hole can dominate the energy output of its entire galaxy, reshaping the environment around it, preventing star formation, enriching intergalactic space with energy and material. These are not passive objects sitting quietly at galactic centers. When active, they're among the most powerful phenomena in the cosmos. Black hole activity was more common in the early universe when galaxies were forming and merging more frequently. Looking back in time, which we do by looking at distant objects whose light has taken billions of years to reach us, astronomers see more quasars and active galactic nuclei. The universe's earlier epochs were more violent, with more galaxy collisions, more gas available for accretion, more vigorous black hole feeding. The peak of black hole activity seems to have occurred when the universe was about 3 to 4 billion years old. Since then, things have calmed down. Galaxy mergers have become less frequent as the universe has expanded and galaxies have moved apart. Gas has been consumed in star formation, or heated and expelled from galaxies. There's less fuel readily available for black holes to consume. Most supermassive black holes today, like our own Sagittarius A, are relatively quiet, sipping rather than gulping, emitting only weak radiation from occasional infall of gas or stars. This evolution tells a story. The universe has aged from a violent youth into a calmer middle age. Black holes, once blazing as quasars, have settled into quieter states. They're still there, still massive, still capable of activity if fed. But the abundant fuel of earlier epochs is largely gone. Looking at distant quasars is like looking at photographs of your grandparents in their youth, seeing a more vigorous, energetic version of what has since settled into stillness. Some black holes form in binary pairs, orbiting each other for millions or billions of years before merging. Not all black holes are solitary. In some cases, two massive stars in a binary system both end their lives as black holes, creating a binary black hole system. These two black holes orbit their common center of mass, bound together by gravity, circling each other like cosmic dancers. The separation might be thousands of kilometers or astronomical units, or even light years, depending on the original stellar binary's properties. These binaries can persist for immense timescales. If the black holes are widely separated and relatively isolated, they might orbit each other for billions of years with little change. But if there's matter around, or if they're embedded in a dense stellar environment, interactions gradually drain energy from the orbit. The black holes slowly, inexorably, spiral closer together. The process is patient, operating over timescales far longer than human civilization has existed. Eventually, when the separation has decreased enough, gravitational wave emission becomes the dominant mechanism removing energy from the orbit. The inspiral accelerates dramatically. What took millions or billions of years now happens in hours, then minutes, then seconds. The black holes spiral together at increasing speeds, emitting gravitational waves of increasing frequency and amplitude, until finally they merge in a fraction of a second. The long wait ends in a sudden, violent union. There are likely hundreds of millions of stellar mass black holes in our galaxy alone. The Milky Way has existed for over 13 billion years, forming stars throughout that time. Many of the most massive stars have already lived their brief, brilliant lives and died, some as supernovae that left black holes behind. Conservative estimates suggest there could be 100 million stellar mass black holes in our galaxy. Some estimates run higher, perhaps several 100 million. Most of these black holes are invisible and undetectable, at least with current technology. They're not feeding on anything, so they're not glowing with X-rays. They're not part of binary systems where we could detect orbital motion. They're simply dark, massive objects drifting through the galaxy, invisible witnesses to the Milky Way's long history. They might occasionally disturb the orbits of passing stars or gravitationally lens background light. But these events are rare and hard to detect. Think about that for a moment. Hundreds of millions of black holes scattered throughout our galaxy like dark seeds. Some might be relatively close to us, astronomically speaking, perhaps just tens of light years away. We wouldn't know. They're silent, dark, patient. They remind us that for all we've learned about the cosmos, much remains hidden. The visible universe is just a fraction of what exists. Black holes help distribute heavy elements throughout galaxies through their jets and outflows. When black holes feed, not everything falls in. Some material gets heated to such extreme temperatures that it's ejected in winds and jets, traveling at thousands or tens of thousands of kilometers per second. This material has often been enriched with heavy elements: carbon, oxygen, iron, and heavier elements created in stars and supernova that ended up in the accretion flow. These outflows carry enriched material far from the black hole, sometimes all the way out of the galaxy into intergalactic space. Over cosmic time, this process helps distribute heavy elements throughout and beyond galaxies. Elements created in stellar cores, forged in supernova explosions, are given one final journey by black hole-driven winds, spreading across vast volumes of space. This enrichment matters for future generations of stars and planets. Gas clouds enriched with heavy elements cool more efficiently, fragment differently, form different types of stars. The heavy elements become raw material for rocky planets, and eventually for life. In a poetic sense, black holes help seed the universe with the elements necessary for complexity, distributing the periodic table across cosmic distances through their powerful outflows. The total mass of a galaxy's central black hole is typically about 0.1% of the mass of the galaxy's central bulge. This ratio, roughly 1 part in 1,000, holds across galaxies of vastly different sizes. Small galaxies with small bulges have proportionally smaller black holes. Giant elliptical galaxies with massive bulges have correspondingly massive black holes. The relationship isn't perfect. There's scatter individual variations, but the average ratio remains remarkably consistent. The precision of this ratio is one of the most striking empirical facts about black holes and galaxies. It suggests a regulatory mechanism, some process that ensures black holes don't grow too large or remain too small relative to their host galaxies. This is part of the coevolution we discussed earlier, the black hole and bulge influencing each other's growth to maintain this balance. What's also interesting is that this relationship specifically involves the bulge, not the entire galaxy. Disk galaxies like the Milky Way have both a flat disk and a central bulge. The black hole mass correlates with the bulge mass, not the total. This suggests that the physical processes linking black hole and galaxy growth operate primarily in the central regions in the bulge, where gas can more easily reach the black hole and where the black hole's influence is strongest. Some black holes are wandering through galaxies, displaced from centers during galaxy mergers. When two galaxies merge, their central black holes eventually sink toward the center of the merged galaxy. But this process can leave some black holes stranded. Perhaps one galaxy had multiple black holes, a central one plus others from previous mergers. Perhaps the merger dynamics were complex, with 3 or more black holes involved. In these cases, some black holes can end up on eccentric orbits far from the new galactic center, or even ejected entirely. These wandering black holes drift through the galaxy, no longer at the center, no longer surrounded by abundant gas. They're orphans, displaced from their original homes, moving through the stellar population. If they encounter gas clouds or star clusters, they might briefly feed and become detectable. Otherwise, they remain dark and hidden. Finding these wandering supermassive black holes is difficult but not impossible. Astronomers look for off-center sources of X-rays or radio emission, unusual kinematic signatures in gas, or gravitational effects that don't match the galaxy's visible mass distribution. Each detection provides clues about the galaxy's merger history, revealing past collisions and disruptions. These wanderers are cosmic evidence that galaxy evolution isn't always smooth and ordered, but can be messy and chaotic. Black holes can trigger star formation in some circumstances by compressing gas clouds with their jets. We've discussed how black hole feedback can suppress star formation by heating gas. But there's another side to this story. Sometimes, the shock waves driven by jets can actually trigger star formation. When a jet plows into a gas cloud, it compresses the gas at the shock front. If conditions are right, this compression can cause the gas to collapse and fragment, forming new stars. Observations show this happening in some galaxies, along the edges of jets or in regions where jets impact dense clouds. There are sometimes young stars, evidence of recent star formation triggered by the jet's passage. It's a reminder that astrophysical feedback isn't simple. The same processes that suppress star formation in one context can trigger it in another. This positive feedback is probably less common than suppression, and the net effect of black hole activity is likely to reduce overall star formation. But these pockets of triggered star formation exist, creating complex patterns where some regions are forming stars vigorously while others are quenched. The interplay of jets, gas, and star formation creates intricate structures that we're still working to understand in detail. The nearest quasar is about 600 million light-years away. All the nearby supermassive black holes are relatively quiet. In our cosmic neighborhood, the nearby galaxies, within a few 100 million light-years, there are no blazing quasars. The nearest quasars are at least 600 million light-years distant, well outside our local volume of space. All the supermassive black holes nearby, in the Milky Way, Andromeda, and neighboring galaxies, are in relatively quiet states, not actively feeding at the high rates that would make them quasars. This tells us something about our local environment and cosmic time. The era of vigorous quasar activity has largely passed. We live in a quieter epoch, where galaxy mergers are less frequent, where much of the available gas has already been consumed or heated, where black holes have settled into dormancy. The universe's wild youth is behind us, at least in this corner of space. If we want to study quasars, we have to look far away, and thus far back in time. The most powerful quasars exist in the distant universe, billions of light-years away. Their light showing us what the cosmos was like billions of years ago. We see them not as they are now, but as they were when the universe was younger, more active, more violent. Our neighborhood has grown calm, and that calmness speaks to the age and evolution of our cosmic surroundings. Matter falling into a black hole becomes part of it forever, from our perspective. The black hole grows with each meal. Every particle that crosses the event horizon adds to the black hole's mass. A single atom, a dust grain, an entire star, whatever falls in is incorporated, increasing the black hole's mass and slightly expanding its event horizon. This growth is permanent. From the perspective of the outside universe, that mass is gone, absorbed into the black hole forever. Over the lifetime of a black hole, countless particles have made this one-way journey. Stars passing too close, gas clouds swept up, photons absorbed. Each contribution, however small, adds to the total. Active black holes can grow substantially over millions of years of feeding. Even quiet black holes grow, albeit slowly, from occasional infall. This accumulation means each black hole carries within it the history of everything it's ever consumed. Not that we can read that history. The no-hair theorem says all that information is hidden behind the event horizon. But in a sense, the black hole is a tomb, a repository of all the matter and energy that has ever fallen in. It's grown heavier with age, larger, incorporating more of the universe into its event horizon with each passing eon. Black holes create some of the most extreme magnetic fields in the universe around their accretion disks. The accretion disks around black holes aren't just hot gas. They're highly ionized plasma threaded with magnetic fields. As the disk rotates, it can amplify these magnetic fields through a process called the magnetorotational instability, creating fields of tremendous strength, millions or even billions of times stronger than Earth's magnetic field. These intense magnetic fields play crucial roles. They create turbulence in the disk, helping transport angular momentum outward and allowing matter to fall inward. They channel material into jets, focusing the outflow along the black hole's rotational axis. They accelerate particles to relativistic speeds, creating the high-energy radiation we observe. The magnetic field becomes a key player in the disk's structure and evolution. Studying these magnetic fields directly is challenging. They're far away, and magnetic fields don't emit light directly. But we can infer their presence from the radiation they produce, from the polarization of light emitted by the disk, from the structure of jets. These fields represent some of the most extreme magnetic environments in the universe, testing our understanding of plasma physics and magnetohydrodynamics under conditions we could never reproduce in laboratories. The study of black holes has led to advances in our understanding of space-time, quantum mechanics, and thermodynamics. Black holes are more than astrophysical objects. They're theoretical laboratories where our deepest physical theories meet and sometimes conflict. General relativity predicts their existence and describes their classical behavior. Quantum mechanics suggests they radiate through Hawking radiation and raises the information paradox. Thermodynamics applies to them through the laws of black hole mechanics, where horizons have temperature and entropy. The attempt to understand black holes fully has driven theoretical physics forward. The information paradox has inspired new ideas about quantum gravity, holography, and the nature of space-time. Black hole thermodynamics has revealed deep connections between gravity, quantum mechanics, and thermodynamics, three areas once thought largely independent. The study of singularities has pushed mathematicians to develop new techniques and theorems. In this sense, black holes are gifts to physics. They're places where our theories are pushed to their limits, where inconsistencies and gaps become apparent, where new physics might be hiding. By studying them, we learn not just about these specific objects, but about the fundamental nature of reality itself. They're cosmic teachers, posing questions that challenge us to think deeper and reach further in our understanding. We don't know what happens to information that falls into a black hole, a puzzle called the information paradox. In quantum mechanics, information is sacred. The laws governing particles and fields are reversible. If you know the current state of a system perfectly, you can, in principle, calculate both its past and its future. Information about quantum states is never truly destroyed. It might become scrambled, spread out, encoded in subtle correlations, but it persists. This is called unitarity, and it's a cornerstone of quantum theory. But black holes seem to violate this principle. When something falls into a black hole, all its detailed quantum information, the precise state of every particle, every field, appears to be lost behind the event horizon. If the black hole eventually evaporates through Hawking radiation, and that radiation is purely thermal with no information encoded in it, then the information is gone, destroyed, erased from the universe. This creates a fundamental conflict between quantum mechanics and general relativity. One of them must be wrong or incomplete, or our understanding of what happens must be missing something crucial. Perhaps information does escape, encoded in the Hawking radiation, in ways too subtle for us to detect yet. Perhaps the evaporation process isn't what we think. Perhaps information is preserved but inaccessible, stored in some remnant or in correlations we don't understand. The paradox remains one of the deepest puzzles in theoretical physics, a question about whether the universe truly keeps records of everything, or whether some things can be irretrievably lost. The singularity at a black hole's center might not be a physical thing at all, but a sign our theories need revision. When general relativity predicts a singularity, a point of infinite density and curvature, it's almost certainly telling us that the theory has reached its limits. Infinities in physics are usually red flags, signals that you're asking questions the theory can't answer, that you need new physics to proceed. The singularity might be real, or it might be an artifact of applying general relativity where it no longer applies. At the scales and energies expected near the singularity, quantum effects should become important. Space-time itself might fluctuate, becoming foamy and uncertain. The very notions of smooth geometry and continuous space-time might break down. We'd need a theory of quantum gravity, a framework that unifies quantum mechanics and general relativity, to describe what actually happens there. String theory, loop quantum gravity, and other approaches to quantum gravity each offer different pictures of what might replace the singularity. Maybe it's a region of highly curved but finite space-time. Maybe it's a quantum fuzzball of strings. Maybe it's something we haven't imagined yet. The singularity, in this view, is less a physical prediction and more a signpost saying new physics here, pointing us toward questions we need to answer to complete our understanding of nature. Some theories propose that the inside of a black hole could contain an entire separate universe. This is speculative, existing more in the realm of theoretical possibility than established physics, but it's an intriguing idea. If space-time inside a black hole becomes disconnected from our universe in some sense, and if conditions near the singularity involve something like a Big Bang in reverse, perhaps what looks like a singularity from outside is actually a Big Bang from inside, the birth of a new, expanding universe. We could never verify this directly. Any universe inside a black hole would be causally disconnected from ours. No signal could pass from it to us. No traveler could return with tales of what they found. It would be truly another universe, completely separate, sharing no causal connection with our reality once the event horizon formed. The idea plays with notions of cosmic reproduction, where black holes might spawn baby universes, creating a multiverse through gravitational collapse. It's beautiful, strange, and currently untestable. But it reminds us that the inside of a black hole is genuinely unknown territory. We can speculate, build mathematical models, explore possibilities, but we're fundamentally limited in what we can observe. The event horizon is an informational barrier that might hide realities stranger than we can currently imagine. Black holes might be connected to other black holes or distant regions of space through wormholes. The mathematics of general relativity allows for wormholes, tunnels through space-time connecting distant regions or even different universes. Some solutions to Einstein's equations describe black holes connected by these bridges, called Einstein-Rosen bridges. A black hole here and a black hole there, linked by a shortcut through the geometry of space-time. But before you imagine traveling through one, there are complications. The wormholes in these classical solutions are unstable. They pinch off almost immediately, closing before anything could pass through. They'd also require exotic matter with negative energy to hold them open, something we've never found in nature. Even if traversable wormholes could exist, crossing one might involve lethal tidal forces or other hazards. Recent developments in quantum information theory have suggested intriguing connections between quantum entanglement and wormhole geometry. The idea that quantum correlations between particles might be geometrically related to space-time connections. This ER-EPR conjecture links Einstein-Rosen bridges with Einstein-Podolsky-Rosen entanglement, suggesting deep relationships between quantum mechanics and geometry. It's speculative, actively researched, and might point toward new understandings of how space-time emerges from quantum information. But for now, wormholes remain theoretical constructs, fascinating possibilities that might or might not reflect reality. The true nature of what happens at the singularity requires a theory of quantum gravity we don't yet have. This is where our journey into black holes reaches its current boundary. General relativity breaks down at the singularity. Quantum mechanics doesn't include gravity properly. We need a theory that encompasses both quantum gravity, and we don't have a complete, tested one yet. String theory, loop quantum gravity, and other approaches each offer frameworks, but none is definitively confirmed by experiment. Until we have quantum gravity, we can't truly describe what happens at the singularity or in the extreme conditions near it. We can't say whether singularities are physical or mathematical artifacts. We can't fully resolve the information paradox. We can't answer whether black holes are truly black or whether Hawking radiation carries information. These questions sit at the frontier of physics, waiting for the next theoretical breakthrough. And perhaps that's fitting. Black holes have always pushed us to the edges of understanding, forcing us to grapple with concepts that challenge intuition and require new mathematical tools. They've been among the most important theoretical objects in physics, precisely because they pose such difficult questions. The fact that some mysteries remain isn't a failure. It's an invitation to the next generation of physicists to develop the tools and insights needed to peer deeper into these cosmic enigmas. Some physicists propose that black holes might eventually transform into white holes that expel matter. White holes are the time-reversed solutions to the equations that describe black holes, where a black hole has an event horizon that allows matter to fall in but not come out. A white hole would have a horizon that allows matter to come out but not fall in. It's a region that expels matter and energy, the opposite of a black hole in every way. Mathematically, they're equally valid solutions to Einstein's equations. But do white holes exist in nature? We've never observed one, and it's hard to imagine how one would form. Some speculative theories suggest that black holes might, after unimaginably long times or through quantum processes we don't understand, transform into white holes. The singularity might bounce, reversing the collapse, expelling the matter that fell in across cosmic timescales. This remains highly speculative. existing more in theoretical explorations than in mainstream physics. White holes raise causality questions. How could something expel matter that just happens to avoid falling in from the outside? But they remind us that the mathematics of space-time allows for stranger possibilities than we've observed. Perhaps white holes exist in some inaccessible region of the cosmos, or perhaps they're purely mathematical curiosities. Either way, they represent the kind of strange mirror image solutions that general relativity permits. The holographic principle suggests all the information about a volume of space can be encoded on its boundary. Black hole thermodynamics revealed something strange. The entropy of a black hole, a measure of information content, is proportional to the area of its event horizon, not its volume. This is counterintuitive. In normal thermodynamics, entropy depends on volume, but for black holes, it's the surface area that matters. A black hole's information capacity is determined by the area of its boundary. This observation led to the holographic principle, a profound idea suggesting that the information in any region of space can be encoded on its boundary. The three-dimensional volume we experience might be, in some sense, a projection from information stored on a two-dimensional surface. Reality as a hologram, with one dimension being somehow emergent rather than fundamental. This principle has become central to modern theoretical physics, influencing approaches to quantum gravity and our understanding of space-time itself. It suggests that what we perceive as three-dimensional space might not be the deepest description of reality. The universe might be fundamentally holographic, with black holes providing the crucial clue that led us to this realization. It's a profound shift in perspective, one that's still being explored and developed in cutting-edge research. We may never know if anything can exist or survive inside a black hole. It's forever beyond our ability to observe. The event horizon creates an absolute observational barrier. Once something crosses it, no information can return to us. We can theorize, calculate, build models of what might exist inside, but we can never observe it directly. We can't send a probe and get data back. We can't wait for information to eventually escape. The horizon is a one-way membrane in space-time, and it's absolute. This creates a unique situation in science. We can study black holes from the outside, measure their effects, test predictions about their observable properties, but their interiors remain fundamentally inaccessible. Any claims about what exists inside, whether it's a singularity, quantum foam, another universe, or something else entirely, can never be empirically verified through direct observation. Perhaps this is the ultimate mystery black holes offer us. Not just difficult questions, but questions that might be permanently beyond our ability to answer through observation. We can calculate, theorize, reason mathematically, but we hit a wall at the event horizon, a boundary not just in space, but in the very possibility of knowledge. It's a humbling reminder that the universe contains regions that are, in principle, unknowable to outside observers. Black holes represent the ultimate limit of density and gravity we can imagine in our universe. Nothing in the known universe is more extreme than a black hole. No higher densities exist outside singularities. No stronger gravitational fields are possible within our current physics. They represent the endpoint, the maximum distortion of space-time that can exist before an event horizon forms and seals the extreme conditions off from the rest of space. You can't have a gravitational field stronger than a black hole's without creating a black hole. You can't compress matter denser than a black hole without forming one. They're the limiting case, the edge of possibility within general relativity. Everything less extreme than a black hole is permitted. Anything more extreme becomes a black hole. This makes them natural laboratories for extreme physics. The event horizon marks the boundary where space-time curvature reaches its maximum for a given mass concentration. Just outside, conditions are as extreme as they can be, while still allowing information to escape. At the horizon and beyond, we cross into territory where our usual notions of space and time transform into something else. Black holes don't just exist at physical extremes. They define those extremes, marking the limits of what's possible in our universe. Despite all we've learned, black holes remain fundamentally mysterious, objects that push physics to its limits and invite us to wonder. We've learned so much. We've detected them through X-rays and gravitational waves. We've imaged their shadows. We've measured their masses and spins. We've tracked stars orbiting them and watched galaxies evolve around them. We've developed sophisticated theories describing their behavior and profound connections between them and fundamental physics. And yet, mysteries remain. The information paradox, the nature of singularities, the precise mechanisms of jet launching, the details of how they co-evolve with galaxies, whether primordial black holes exist, what truly happens at the event horizon from the perspective of an infalling observer, how quantum gravity modifies their structure, whether their interiors contain anything we would recognize. Perhaps this enduring mystery is what makes black holes so captivating. They sit at the intersection of what we know and what we don't, constantly challenging us to understand more deeply, to develop better theories, to ask more refined questions. They're cosmic puzzles that reward study with insight, but always hold something back, always keep some secret behind the event horizon. They invite wonder, contemplation, and the recognition that the universe is stranger and more beautiful than our everyday experience suggests. And as you drift toward sleep, perhaps you can carry that sense of wonder with you. The knowledge that out there in the cosmic dark, these extraordinary objects exist, warping space-time, challenging physics, and quietly keeping their deepest secrets. And so we've traveled through 100 facts about black holes, from their theoretical prediction to their observation, from their violence to their gentleness, from what we know to what we can only wonder about. We've explored objects that bend space-time, trap light, emit nothing yet can outshine galaxies, evaporate over eons yet grow with each meal. Black holes remind us that the universe operates on scales and principles far removed from daily experience. They show us that gravity, given enough mass and concentration, can transform space and time into something almost unrecognizable. They teach us that reality is stranger than intuition suggests, that mathematics can predict phenomena we couldn't imagine, that observation eventually confirms even the most unlikely theoretical predictions. But perhaps most importantly, they invite us to wonder, to sit with the mystery of what lies beyond an event horizon, to contemplate time slowing and stopping, to imagine matter compressed to infinite density, or quantum states too complex to fully describe, to recognize that for all our knowledge, the universe still holds secrets, some perhaps permanently beyond our reach, sealed behind horizons we can never cross. As you close your eyes tonight, you might find some comfort in knowing that black holes exist, that the universe is vast enough and old enough and strange enough to contain these objects. That far away, at the center of our galaxy, Sagittarius AA sits quietly, a 4 million solar mass testament to cosmic extremes. That throughout the universe, hundreds of billions of black holes exist, from stellar remnants to supermassive giants, each one a marvel of physics, each one a mystery. Sleep well, knowing the cosmos is more wonderful than we can fully grasp. Let the mysteries linger gently in your thoughts, and perhaps in dreams you'll find yourself falling, not toward darkness, but toward understanding, toward that quiet place where wonder and rest meet. Good night.